Microscopic metal spheres buried in 65-million-year-old rock match signatures from modern nuclear tests. Scientists discovered these anomalies while investigating a disturbing question: what if we weren't Earth's first civilization? The spheres themselves measure between 10 and 100 micrometers in diameter, roughly the width of a human hair. Geologists found them embedded in the KPG boundary layer, the same geological marker that records the asteroid impact that killed the dinosaurs. What made these spheres extraordinary wasn't their size or location, but their composition. The spheres represented a genuine mystery, one that challenged fundamental assumptions about Earth's deep history and raised an uncomfortable question. Had someone or something been conducting nuclear reactions 65 million years ago? The metallic structures contained isotopic ratios of uranium, plutonium, and other heavy elements that don't occur naturally in those proportions. When researchers compared the signatures to known geological processes, nothing matched. Then someone suggested comparing them to something else entirely: the residue from nuclear weapons testing. The match was undeniable. Modern nuclear detonations produce microscopic spherules through the intense heat and pressure of the blast, which vaporizes surrounding material and causes it to condense into tiny metallic beads as it cools. These spherules carry specific isotopic fingerprints based on the fission process. The 65-million-year-old spheres displayed nearly identical characteristics. The implications sent shockwaves through the scientific community. If these weren't natural formations, and if they genuinely resembled nuclear byproducts, then something had generated temperatures exceeding 2,000 degrees Celsius and pressures found only in the most extreme events. The asteroid impact could account for some of this, but the specific isotopic patterns suggested something more targeted, more controlled. Dr. Elena Vasquez from the Institute of Geological Sciences led the analysis team. Her laboratory ran the samples through mass spectrometry dozens of times, checking for contamination, verifying the dating, and eliminating every possible alternative explanation. The spheres were definitely 65 million years old, definitely contained the unusual isotopic signatures, and definitely shouldn't exist according to conventional understanding. Other research teams found similar anomalies in rock cores from 3 different continents, all from the same time period. The distribution pattern was puzzling. Rather than being scattered randomly as asteroid debris would be, the spheres appeared in concentrated deposits at specific locations. Some sites had thousands of spheres per cubic centimeter of rock, while nearby areas had none. This clustering suggested point sources rather than global dispersion. The debate intensified when physicists calculated the energy requirements needed to produce such signatures. Natural radioactive decay couldn't generate the specific isotope ratios found in the spheres. Cosmic radiation was ruled out. Volcanic activity, hydrothermal vents, and lightning strikes all failed to match the evidence. The only known process that could create these exact characteristics was nuclear fission under controlled conditions. Critics argued that unknown geological processes might be responsible, that science simply hadn't discovered the natural mechanism yet. But as more data accumulated, that explanation grew weaker. The nuclear spheres weren't the only anomaly forcing scientists to reconsider Earth's timeline. In 2018, astrophysicist Adam Frank and climatologist Gavin Schmidt published a paper that would fundamentally challenge how researchers thought about ancient civilizations. The Silurian Hypothesis gained traction because it aligned with emerging discoveries that didn't fit conventional narratives. The nuclear spheres were one example. Researchers also documented other anomalies: unexplained extinction events that coincided with sudden climate shifts, mysterious chemical signatures in ancient rock that resembled industrial pollution, and geological formations that seemed to show evidence of rapid, intense heating beyond what natural processes could explain. The hypothesis forced scientists to develop new frameworks for identifying potential technosignatures in the geological record. What would advanced technology look like after millions of years of degradation? How could researchers distinguish between natural phenomena and the remnants of artificial processes? These questions opened entirely new fields of investigation. Some dismissed the Silurian hypothesis as speculation without merit, but others recognized its value in challenging assumptions. If scientists couldn't definitively rule out previous civilizations on Earth, what did that mean for the search for life elsewhere? If industrial civilizations left such faint traces, detecting alien technology across vast cosmic distances might be far more difficult than anyone imagined. The hypothesis didn't provide answers, but it asked the right questions, and those questions led researchers back to anomalies like the nuclear spheres with fresh perspectives and new urgency. They called it the Silurian Hypothesis, named after an intelligent reptilian species from the British science fiction series Doctor Who. The premise was deceptively simple. If an industrial civilization had existed on Earth millions of years before humans, would we even be able to detect it? The answer was far more unsettling than most scientists expected. Frank and Schmidt weren't claiming that ancient civilizations definitely existed. Instead, they were exposing a massive blind spot in scientific thinking. Researchers had always assumed that evidence of civilization would be obvious and permanent, but the data told a different story. Modern human industrial civilization has existed for roughly 300 years, a geological eye blink. In the 4.5 billion year history of Earth, that represents 0.0000067% of the planet's existence. If humanity vanished tomorrow, what traces would remain after 65 million years? The researchers worked backward from this question, examining what geological signatures our civilization would leave behind. Cities would erode into dust within thousands of years. Steel and concrete would corrode and crumble. Plastics would break down into microparticles and eventually degrade completely. Even our most durable structures, things like Mount Rushmore or the pyramids, would be ground to powder by the relentless forces of plate tectonics, erosion, and geological recycling. Within a few million years, nearly every physical artifact of human existence would disappear, but some signatures might persist. The researchers identified several potential markers: unusual spikes in carbon isotopes from fossil fuel burning, elevated concentrations of synthetic chemicals, radioactive isotopes from nuclear testing, and changes in sediment composition from mass agriculture and mining. These chemical fingerprints could theoretically survive in rock layers for millions of years. The problem was detection. Finding a thin layer of unusual chemistry in billions of years of geological record would be like searching for a single page in a library containing every book ever written, except the library is buried underground and most of the books have been destroyed. The odds of randomly drilling a core sample that intersected with evidence from a previous civilization were astronomically small. This realization forced an uncomfortable conclusion. Absence of evidence wasn't evidence of absence. The fact that scientists hadn't found proof of ancient civilizations didn't mean they never existed. It might simply mean that the evidence was too subtle, too degraded, or too localized to detect with current methods. The geological timescale reveals a staggering truth that most people never consider. Earth's 4.5 billion year history is so vast that human comprehension fails to grasp its true scale. If the entire history of Earth were compressed into a single 24-hour day, modern humans would appear in the last 1.2 seconds before midnight. Consider the practical implications. If an industrial civilization existed 200 million years ago and lasted 100,000 years, finding evidence would require drilling a core sample that intersected exactly the right location and exactly the right thin layer of rock corresponding to that specific 100,000-year window. The odds of randomly hitting that target are comparable to throwing a dart at a map of Earth and hitting a specific building in a specific city. Researchers would need to know where to look before they started looking, but without prior evidence, they have no way to target their search. The spatial distribution problem mirrors the temporal one. Ancient civilizations might have been concentrated in specific regions, just as modern industrial activity clusters around certain areas. If those regions have since been subducted beneath tectonic plates, buried under miles of sediment, or eroded away completely, the evidence would be gone. The ocean floor, which covers 71% of Earth's surface, is geologically young, constantly recycled through seafloor spreading. Any evidence of coastal or oceanic civilizations older than 200 million years has been destroyed. Continental regions fare better, but even there, erosion and deposition constantly reshape the landscape. Mountain ranges rise and erode away. River valleys fill with sediment. Coastlines advance and retreat. The Earth of 100 million years ago had a completely different geography than today. Continents were in different positions. Oceans covered different areas. Climate zones were shifted. A thriving civilization in what is now the Sahara Desert might have existed when that region was lush forest, and all traces would now be buried under sand or eroded away entirely. This geological amnesia affects all evidence equally. Fossils, artifacts, chemical signatures, everything faces the same challenges of preservation and discovery. The fossil record itself demonstrates this limitation. Paleontologists estimate that less than 0.01% of all species that ever lived have been discovered as fossils. The vast majority left no trace whatsoever. If biological organisms, which existed for millions of years and numbered in the billions, rarely fossilize, the chances of finding artifacts from a brief technological civilization are exponentially smaller. The conclusion is mathematically unavoidable. Earth's geological record has the resolution and coverage to definitively rule out civilizations only within the last few million years, and even then, only in well-studied regions. Beyond that window, the planet's history becomes increasingly opaque. Hundreds of millions of years, perhaps billions, remain essentially invisible to current detection methods. In that vast expanse of hidden time, entire worlds could have risen and fallen, leaving behind only the faintest chemical whispers in scattered rock layers, if they left anything at all. All of recorded human history, every empire, every war, every technological achievement would occur in the final 0.2 seconds. Industrial civilization would exist for less than 1,000th of a second. This compression exposes the central problem with detecting ancient civilizations. The resolution of geological time is far too coarse to capture brief technological periods. Geologists divide Earth's history into eons, eras, periods, and epochs, but even the smallest standard divisions span millions of years. The Holocene epoch, which encompasses all of human civilization, is defined as the last 11,700 years. In geological terms, this entire span is treated as a single moment, an indivisible unit of time. Any civilization that rose and fell within a similar time frame millions of years ago would be compressed into the same geological instant, invisible within the resolution of the rock record. The problem compounds when examining how geological data is actually collected. Scientists don't have continuous records of Earth's history. Instead, they work with fragmentary samples, drill cores from ocean floors, exposed rock faces in canyons, ice cores from Antarctica, These samples represent tiny fractions of specific locations at specific times. Most of Earth's geological record has been destroyed, subducted beneath tectonic plates, eroded away, or remains buried and inaccessible. Estimates suggest that less than 1% of all sedimentary rock that ever formed still exists today. The rest has been recycled through geological processes, melted in the mantle, or weathered into unrecognizable particles. This means that 99% of Earth's physical history has been permanently erased. Even within the remaining 1%, coverage is sporadic and uneven. Some periods have extensive rock records, others have almost nothing. The further back in time researchers look, the more fragmentary the evidence becomes. Rocks older than 3 billion years are exceptionally rare. Rocks older than 4 billion years are almost non-existent. Entire chapters of Earth's history exist as blank pages. The temporal resolution problem creates another layer of difficulty. When geologists date rock layers, they typically work with margins of error spanning hundreds of thousands or even millions of years. A rock layer dated to 100 million years ago might actually be anywhere from 99.5 to 100.5 million years old. Within that million-year margin of error, dozens of civilizations could have risen and fallen, each lasting as long as human civilization has existed, and they would all be indistinguishable in the geological record. They would appear as a single moment in time. The fossil record contains a deception that most people never recognize. It presents a curated gallery of Earth's past life, not a comprehensive archive. What appears in museums and textbooks represents an infinitesimally small fraction of organisms that actually existed, survivors of a preservation lottery so improbable that paleontologists consider every fossil a minor miracle. This represents perhaps 0.0001% of the dinosaurs that actually lived. The vast majority left no trace whatsoever. The situation worsens for organisms that lived in environments hostile to fossilization. Mountain dwellers rarely fossilize because erosion dominates those environments rather than deposition. Forest organisms decay too quickly on the organic-rich soil. Desert organisms are scattered by wind and scavenged completely. Open ocean organisms sink into abyssal depths where their remains dissolve or are consumed. Even when fossilization succeeds, the resulting fossil typically preserves only hard parts: bones, teeth, shells. Soft tissues, organs, skin, and feathers rarely survive. Behavior, social structures, technology use, and intelligence leave no direct fossil evidence. If ancient humans are judged solely by their fossilized bones, nothing indicates they built cities, created art, or developed language. The skeleton alone reveals almost nothing about civilization. This creates a profound problem for detecting ancient technological species. If paleontologists struggle to find fossils of abundant organisms that lived for millions of years, finding evidence of a rare, short-lived intelligent species becomes nearly impossible. A technological civilization might have consisted of millions of individuals, but if they existed for only 100,000 years in a localized region, the probability of any individual fossilizing approaches zero. Even if fossilization occurred, the probability of humans finding that fossil in the narrow window before erosion destroys it is equally minuscule. Consider the implications for artifacts. Bones and shells are composed of minerals naturally resistant to decay, yet they rarely fossilize. Artificial materials like metals, plastics, and concrete are less stable over geological time. Metals oxidize and disperse, plastics photodegrade and fragment into particles that scatter, concrete crumbles as water infiltrates and freezes, glass eventually devitrifies and weakens. None of these materials are designed to survive millions of years of geological processes. Even if artifacts were buried in ideal conditions, they would likely be unrecognizable after deep time. A metal tool would become a rust stain, a concrete foundation would become a layer of calcite and aggregate, a plastic container would become a thin film of organic residue. Without context, these traces would be indistinguishable from natural geological features. The only materials that persist are those already similar to natural minerals. Ceramics might survive as odd clay fragments, but they would be nearly impossible to distinguish from natural clay deposits without microscopic analysis. The fossil record's incompleteness extends beyond individual organisms to entire ecosystems. Paleontologists have identified numerous gaps where ecosystems seem to vanish completely, then reappear millions of years later with no transitional forms. These gaps don't necessarily represent mass extinctions or sudden evolutionary leaps. More likely, they represent periods where conditions didn't favor fossilization, creating blank chapters in Earth's biological history. If entire ecosystems can disappear from the fossil record despite consisting of billions of organisms living for millions of years, a single technological species existing briefly would vanish far more completely. Understanding why fossilization is so rare reveals why finding evidence of ancient civilizations faces nearly impossible odds. When an organism dies, the default outcome is complete disappearance. Bacteria, fungi, scavengers, and weathering rapidly dismantle organic material, returning it to the ecosystem within weeks or months. The mathematics are unforgiving. Multiply the low probability of fossilization by the low probability of fossil survival by the low probability of discovery, and the result approaches zero. Ancient civilizations face the same preservation lottery as ancient organisms, but with worse odds, because technological species are rarer, shorter-lived, and composed of materials less likely to fossilize than bone and shell. Bones, shells, and other hard parts last longer, but they too eventually crumble into powder and vanish. For fossilization to occur, a precise sequence of unlikely events must happen in rapid succession. First, the organism must die in a location where sediment can quickly bury it, protecting remains from scavengers and decomposition. This immediately eliminates the vast majority of deaths, which occur in environments where burial doesn't happen: open plains, forests, mountainsides, or the open ocean. Second, the burial environment must have the right chemical conditions. Too much oxygen allows bacteria to consume organic material completely. Too much acidity dissolves bones and shells. The sediment must compact into rock without crushing the remains beyond recognition. Groundwater must carry minerals that infiltrate the buried material, gradually replacing organic molecules with stone in a process called permineralization. Each of these conditions must persist for thousands or millions of years without disruption. Third, after fossilization occurs, the rock containing the fossil must survive. Tectonic activity, erosion, metamorphism, and subduction destroy most sedimentary rock over geological time. The fossil must then be re-exposed at Earth's surface through erosion or geological uplift, and this exposure must occur at precisely the moment when humans are present and searching. Finally, someone must actually find the fossil before weathering destroys it, which typically happens within decades of exposure. Paleontologists have calculated the odds. For marine organisms with hard shells, which have the best preservation potential, approximately one individual in a billion becomes a fossil that humans eventually discover. For terrestrial organisms without hard parts, the odds drop to essentially zero. For terrestrial vertebrates with skeletons, estimates suggest 1 in 10 million might fossilize, and 1 in a billion of those might be found. Applying these numbers reveals the scale of loss. Dinosaurs dominated Earth for 165 million years. Yet paleontologists have identified only about 1,000 species from perhaps 100,000 that actually existed. For the entire Mesozoic era spanning 186 million years, fewer than 50,000 individual dinosaur specimens have been discovered worldwide. 252 million years ago, Earth experienced the closest it has ever come to complete sterilization. The Permian-Triassic extinction event eliminated approximately 96% of marine species and 70% of terrestrial vertebrate species, earning it the designation as the most severe biodiversity crisis in the planet's history. Some rock formations show evidence of multiple rapid carbon pulses rather than a single sustained release, suggesting a more complex source than continuous volcanic eruption. Research published in recent years has identified additional anomalies. Certain boundary layer rocks contain elevated concentrations of rare earth elements in ratios that don't match any known volcanic source. Mercury concentrations spike dramatically, which occurs during volcanic events, but the distribution pattern across different geographical locations shows inconsistencies. Some regions that should show strong volcanic signatures based on their proximity to the Siberian traps show weaker signals than more distant locations. Most intriguing are the organic biomarkers preserved in these rocks. Chemical analysis has identified complex hydrocarbon molecules that typically form only under specific industrial processes or during the thermal breakdown of organic materials at temperatures and pressures not commonly associated with natural geological events. These molecules appear in concentrations far higher than background levels, then disappear completely in younger rock layers. The extinction itself shows a pattern of selectivity that puzzles paleontologists. Species that should have been resilient to volcanic gases and temperature changes died out, while some vulnerable species survived. Marine organisms living in deep, cold waters, which should have been buffered from surface temperature changes, went extinct at higher rates than some shallow water species directly exposed to atmospheric changes. Terrestrial plants show a collapse pattern inconsistent with volcanic winter scenarios, dying back rapidly rather than gradually. The recovery period following the extinction also presents mysteries. Life rebounded, but it took nearly 10 million years for biodiversity to approach pre-extinction levels, far longer than recovery from other mass extinctions. Early Triassic ecosystems show bizarre characteristics: stunted organism sizes, low diversity, and unusual dominance by species that would normally be ecological minor players. The planet seemed locked in a degraded state for millions of years, as if the extinction had triggered feedback loops that prevented normal ecosystem recovery. Modern analysis using high-resolution dating techniques has revealed that the extinction may have occurred in multiple pulses, with several distinct die-off events separated by brief recovery periods. This pattern doesn't match well with continuous volcanic activity, but it does match what would occur if multiple environmental thresholds were crossed in sequence, each triggering its own cascade of consequences. The evidence doesn't prove that an ancient civilization caused the Permian-Triassic extinction. Volcanism remains the most parsimonious explanation for most observations. However, the geological signatures from this event demonstrate that industrial-scale atmospheric pollution leaves specific, detectable traces in rock layers that persist for hundreds of millions of years, and that these traces can be remarkably similar regardless of whether their source is geological or technological. What makes this catastrophe particularly unsettling for modern researchers is not merely its scale, but the disturbing similarities between the geological evidence from that ancient apocalypse and the signatures being created by human industrial civilization today. the extinction unfolded with a speed that defies most natural explanations, occurring over a period that geological evidence suggests may have been as brief as 60,000 years, and possibly much faster. In deep time, this represents an instantaneous event, a geological eye blink during which the planet's biosphere collapsed. What caused such rapid devastation remained mysterious for decades, but recent analysis of rock layers from this period has revealed atmospheric changes that follow a pattern eerily familiar to anyone monitoring modern climate data. Carbon isotope ratios preserved in Permian-Triassic boundary rocks show a dramatic negative excursion, indicating a massive injection of carbon-12 into the atmosphere. This signature matches precisely what occurs when organic carbon, stored underground for millions of years, is suddenly released and oxidized. In modern times, this same signature appears when humans burn fossil fuels. The ancient spike was enormous, suggesting that trillions of tons of carbon entered the atmosphere in a geological instant. Temperature proxies from the same rock layers indicate that global temperatures spiked by 8 to 10 degrees Celsius, possibly higher in some regions. Ocean chemistry changed radically, with evidence showing widespread acidification and anoxia, conditions where oxygen levels drop so low that most marine life cannot survive. Sulfur isotope ratios indicate massive releases of hydrogen sulfide, a toxic gas that would have poisoned both ocean and atmosphere. The sequence of changes follows a specific pattern: carbon release, rapid warming, ocean acidification, oxygen depletion, and finally, the release of toxic gases. This cascade mirrors almost exactly what climate scientists predict will occur if human industrial activity continues unchecked, though on a far more extreme scale. The conventional explanation attributes these changes to the Siberian traps, a massive volcanic event that released enormous quantities of greenhouse gases over several 100,000 years. This explanation accounts for much of the evidence, but some aspects remain problematic. The speed of the initial carbon release appears too rapid for volcanism alone. The specific pattern of heavy metal concentrations in boundary layers doesn't match typical volcanic signatures. Carbon isotopes don't lie. When geochemists analyze ancient rock formations, they're reading a chemical diary that records every major atmospheric event in Earth's history with precision that rivals any written document. Some boundary layers show multiple distinct carbon pulses separated by brief intervals, rather than a single sustained release, indicating a more complex mechanism than simple thermal destabilization. The Torsian oceanic anoxic event, approximately 183 million years ago, presents another striking example. Carbon isotope ratios from this period show a sharp negative excursion coinciding with rapid global warming, ocean oxygen depletion, and significant marine extinctions. The isotopic signature indicates release of organic carbon, and the speed of atmospheric change mirrors patterns seen in modern industrial pollution. Volcanic activity in the Karoo-Ferrar Large Igneous Province is typically cited as the cause, with magma intruding through organic-rich sediments and combusting them, releasing their carbon. However, detailed analysis of the carbon release pattern shows irregularities. The isotopic excursion begins before the main phase of volcanic activity, based on radiometric dating of volcanic rocks versus the sedimentary boundary layers. The geographical distribution of the strongest isotopic signals doesn't correlate perfectly with proximity to volcanic centers. Some locations show carbon isotope changes that precede detectable volcanic ash layers by thousands of years. Even more intriguing are smaller, less studied carbon isotope anomalies scattered throughout the geological record. The Aptian oceanic anoxic event at 120 million years ago shows similar patterns. The Cenomanian-Turonian boundary at 94 million years ago displays comparable signatures. Each event shows rapid carbon release, global warming, ocean chemistry changes, and partial biosphere collapse. Each has conventional explanations involving volcanism or methane release, yet each also contains details that don't quite fit these explanations perfectly. High-resolution analysis of these events, made possible by advances in mass spectrometry and dating techniques, has revealed that the carbon release often occurs in discrete pulses rather than continuous flows. Individual pulse events can show carbon injection occurring over periods as short as a few hundred years, far too rapid for most geological processes. The magnitude of these pulses sometimes exceeds what volcanic or methane hydrate sources should be capable of producing in such brief intervals. The isotopic composition occasionally shows mixing patterns that suggest multiple simultaneous sources rather than a single dominant source. Research teams analyzing Cretaceous rock formations have identified at least 7 distinct rapid carbon isotope excursions between 140 and 65 million years ago, each associated with environmental disruption. Not all correspond to known volcanic events or obvious methane release triggers. Some occur during periods of relative geological quiescence, with no clear natural mechanism to explain such massive sudden carbon mobilization. The pattern repeats: rapid carbon-12 enriched release, global warming, environmental stress, then gradual recovery over hundreds of thousands to millions of years. What makes these events particularly relevant to the Silurian hypothesis is that the carbon isotope signature from fossil fuel combustion is essentially identical to signatures that appear in these ancient events. Both involve the rapid oxidation of organic carbon that has been removed from the active carbon cycle for millions of years. Both produce the same distinctive isotopic fingerprint. The ratio between carbon-12 and carbon-13 isotopes preserved in sedimentary layers acts as a fingerprint, revealing not just that carbon entered the atmosphere, but exactly what kind of carbon it was and where it came from. This distinction matters enormously because different carbon sources produce distinctly different isotopic signatures. Both cause the same cascade of environmental consequences. A future geologist examining rock layers from the 21st century would see exactly the same chemical signature that appears in these ancient anomalous events, and would face exactly the same challenge in determining whether the source was geological or technological. The scientific community remains divided on how to interpret these anomalies. Most researchers favor natural explanations, arguing that Earth's geological systems are capable of producing these signatures through volcanism, methane release, or other non-biological processes. However, a growing minority points out that the frequency, magnitude, and pattern of these events suggest something more complex may be occurring. The signatures exist, preserved in stone, undeniable in their chemistry, and consistent in their pattern. They record massive, rapid releases of organic carbon that transformed Earth's atmosphere and climate multiple times throughout history. Whether these signatures represent natural catastrophes or something else entirely remains one of geology's most provocative open questions. Volcanic carbon, released from deep within the Earth's mantle, carries a specific ratio. Carbon from living organisms, which preferentially incorporate the lighter carbon-12 isotope during photosynthesis, carries another. And carbon from fossil fuels, which are ancient organic materials that have been buried and transformed over millions of years, produces yet another distinctive signature. Modern industrial civilization is currently conducting a planet-wide experiment, releasing billions of tons of fossil fuel carbon into the atmosphere annually, and this activity creates an unmistakable isotopic marker that will remain detectable in rock layers for hundreds of millions of years. The signature is so clear that future geologists, should they exist, would be able to identify the Industrial Revolution in sedimentary rocks with absolute certainty. What disturbs researchers investigating the Silurian hypothesis is that this same distinctive signature appears multiple times in Earth's geological record in periods long before humans existed, occurring with a rapidity and magnitude that challenge conventional explanations. The Paleocene-Eocene thermal maximum, which occurred 56 million years ago, shows one of the most dramatic examples. Rock layers from this period reveal a massive negative carbon isotope excursion, indicating that approximately 4,500 to 6,000 gigatons of carbon-12 enriched carbon entered the atmosphere over a period that may have been as short as 5,000 years. The isotopic signature matches what would occur from burning vast quantities of fossil fuels or from the sudden release of methane from organic sources. Global temperatures spiked by 5 to 8 degrees Celsius. Ocean acidification occurred on a massive scale, and deep-sea organisms experienced a significant extinction event. The conventional explanation invokes the release of methane hydrates from ocean sediments, triggered by gradual warming, which then caused runaway heating in a feedback loop. This explanation accounts for much of the evidence, but the speed and magnitude of the initial carbon release remain problematic. Methane hydrate destabilization should occur gradually as warming propagates through ocean sediments. Yet the isotopic evidence suggests a rapid, almost instantaneous injection of carbon. 56 million years ago, Earth's climate system broke. Within a geological instant, global temperatures surged upward by 5 to 8 degrees Celsius, transforming the planet from pole to pole. Arctic regions, previously temperate, became subtropical. Palm trees and crocodilian species migrated to latitudes within the Arctic Circle. Orbital forcing, the gradual changes in Earth's orbit and axial tilt that drive ice age cycles, operates on timescales of tens of thousands of years and produces gradual warming, not sudden spikes. Volcanic activity during this period was not exceptional compared to other epochs that did not experience similar events. Some researchers have proposed that an asteroid impact could have provided the initial shock, but no impact crater of appropriate age has been identified, and iridium concentrations in PETM boundary layers remain at background levels. The speed of the carbon release presents another challenge. Methane hydrate destabilization should propagate gradually as warming diffuses through ocean sediments, which are effective thermal insulators. Heat transfer through sediment occurs slowly, on timescales of thousands to tens of thousands of years. Yet high-resolution analysis of PETM sediments suggests the initial carbon pulse occurred far more rapidly, possibly within centuries. Some boundary sections show evidence of multiple distinct carbon pulses separated by brief intervals of partial recovery, rather than a single sustained release or gradual acceleration. This pulsed pattern is difficult to explain through hydrate destabilization alone, which should produce a more continuous release profile. The geographical distribution of PETM evidence also contains puzzles. The strongest carbon isotope excursions and most severe environmental impacts appear in some regions that are distant from the largest known methane hydrate deposits. Meanwhile, areas directly above major hydrate reserves sometimes show less extreme signatures than expected. The pattern suggests either that methane sources were more widely distributed than current models indicate, or that additional carbon sources contributed to the event. Recent drilling projects have recovered increasingly detailed sediment cores spanning the PETM boundary, allowing researchers to examine the event with unprecedented temporal resolution. These cores reveal complexities that earlier, lower-resolution studies missed. The carbon isotope curve shows fine structure, with multiple smaller excursions superimposed on the main event. Trace element concentrations fluctuate in patterns that don't correlate perfectly with the carbon signal. Some cores show evidence of rapid sediment deposition during the early phase of the PETM, suggesting increased erosion or changes in ocean circulation that preceded the main warming pulse. Oxygen isotope ratios, which record both temperature and the global ice volume, show variations that imply complex changes in the hydrological cycle and possible rapid shifts in precipitation patterns. What makes the PETM particularly relevant to questions about ancient civilizations is that it represents exactly what an industrial civilization's collapse would look like in the geological record millions of years later. The carbon isotope signature matches fossil fuel combustion. The speed of onset matches rapid industrial carbon release. The environmental consequences, global warming, ocean acidification, species extinctions, mirror the changes currently underway from modern human activity. The recovery timescale, hundreds of thousands of years, matches estimates for how long Earth's natural systems would require to reabsorb industrial carbon emissions after civilization ended. Deep ocean temperatures, normally stable over millions of years, increased by 4 to 5 degrees Celsius, even at depths exceeding 1,000 meters. Ocean chemistry shifted dramatically as massive quantities of carbon dioxide dissolved into seawater, dropping pH levels and triggering widespread acidification. If an advanced civilization had existed 56 million years ago and had burned through its fossil fuel reserves before collapsing, the geological signature would be indistinguishable from what we observe in PETM sediments. This parallel does not prove that the PETM was caused by an ancient civilization. Natural explanations remain plausible, and most scientists favor them based on the principle that extraordinary claims require extraordinary evidence. However, the PETM does demonstrate that Earth's geological record contains events that could easily mask evidence of previous industrial activity. The signatures are ambiguous, capable of supporting multiple interpretations. Without additional evidence, such as technological artifacts or artificial isotopes, distinguishing between natural catastrophe and civilizational collapse becomes nearly impossible across such vast timescales. The PETM stands as a stark reminder that Earth's climate system can shift rapidly and dramatically, that massive carbon releases have occurred before, and that the geological record preserves evidence of planetary-scale disruptions, whose causes remain incompletely understood despite decades of intensive research. Between 35 and 50% of benthic foraminifera species, single-celled organisms living on the ocean floor, went extinct within approximately 10,000 years. On land, mammalian species underwent rapid dwarfing, with many lineages shrinking to a fraction of their previous size as they adapted to heat stress and changing vegetation patterns. This event, known as the Paleocene-Eocene Thermal Maximum, or PETM, represents the most rapid and extreme natural global warming event in the past 65 million years. The geological evidence for the PETM appears in sediment cores extracted from ocean floors and continental deposits worldwide. The boundary layer marking this event shows up consistently across the planet, characterized by distinctive clay composition, altered fossil assemblages, and most significantly, that dramatic negative carbon isotope excursion discussed in the previous chapter. The isotopic signature indicates that between 4,500 and 6,000 gigatons of carbon, 12 enriched carbon entered Earth's atmosphere and oceans. To put this in perspective, human civilization has released approximately 1,500 gigatons of carbon since the Industrial Revolution began. The PETM involved roughly 3 to 4 times this amount, released in a period that may have been as brief as 5,000 years, though some estimates suggest it could have occurred in as little as 1,000 years or even less. The recovery period lasted approximately 200,000 years as natural carbon cycle processes gradually removed the excess carbon from the atmosphere. The conventional explanation for the PETM centers on methane hydrates, ice-like compounds of methane and water that exist in vast quantities beneath ocean sediments and within permafrost. According to this hypothesis, gradual warming triggered by orbital variations or volcanic activity destabilized these methane deposits, causing them to decompose and release their methane into the atmosphere. Methane, a potent greenhouse gas, would have caused rapid additional warming, which destabilized more hydrates in a runaway feedback loop. As methane oxidized to carbon dioxide in the atmosphere, it would have produced the carbon isotope signature observed in the geological record, since biological methane is highly enriched in carbon-12. This explanation accounts for many aspects of the PETM, but significant problems remain unresolved. The initial trigger for methane release remains unclear. Deep within sediment cores extracted from locations across the globe, geochemists have discovered something that shouldn't exist. Concentrations of rare earth elements and platinum group metals appearing in geological layers where natural processes cannot adequately explain their presence. These aren't trace amounts scattered randomly through rock. The refining and use of these metals releases them into the environment, where they accumulate in soils, sediments, and water systems in concentrations far exceeding natural background levels. Studies of modern urban sediments show platinum and palladium concentrations elevated by factors of 10 to 100 compared to pre-industrial samples, creating a distinct geochemical signature of industrial civilization. The anomalous ancient concentrations appear in specific stratigraphic contexts that correlate with other unusual geological signals. Some occur at or near mass extinction boundaries, those thin layers marking the transitions between geological periods where fossil assemblages change abruptly. Others appear within sedimentary sequences that show evidence of rapid environmental change. Sudden shifts in depositional environment, changes in sediment grain size or composition, alterations in fossil preservation quality, or the carbon isotope excursions discussed in earlier chapters. The elemental spikes are not uniformly distributed globally, but show geographical patterns suggesting point sources or regional distribution networks rather than uniform global deposition from atmospheric fallout. One particularly intriguing case involves osmium isotope ratios measured in sediments spanning the Paleocene-Eocene thermal maximum. Osmium has two naturally occurring isotopes whose relative abundances differ between mantle-derived material, continental crust, and extraterrestrial sources. During the PETM, osmium isotope ratios shifted toward values indicating an influx of continental crustal material, which researchers initially interpreted as evidence of increased weathering and erosion during the warming event. However, the magnitude and speed of the shift exceed what erosion models predict, and the osmium concentration itself increased beyond what weathering alone should produce. The pattern resembles what would occur if large quantities of osmium-bearing materials from crustal sources were suddenly mobilized and distributed into marine environments through processes more rapid and concentrated than normal weathering. Platinum group metal anomalies also appear in Cretaceous-Paleogene boundary layers, the 66-million-year-old sediments marking the dinosaur extinction. The famous iridium spike at this boundary, discovered in 1980, provided key evidence for the asteroid impact hypothesis. Iridium is a platinum group metal far more abundant in asteroids than in Earth's crust, and its elevated concentration in the boundary clay supported the interpretation of extraterrestrial input. However, detailed analysis reveals that other platinum group metals show more complex patterns. Platinum and palladium concentrations are elevated, but not in the simple ratios expected from chondritic meteorite material. Some locations show platinum enrichment without corresponding iridium increases, while others show the reverse. These are distinct spikes, sharp increases in elemental concentrations occurring within narrow stratigraphic bands, sometimes accompanied by ratios between elements that deviate significantly from crustal averages. These variations have sparked debates about whether multiple sources contributed to the boundary layer geochemistry, whether terrestrial volcanic activity played a larger role than initially recognized, or whether the impact triggered secondary processes that redistributed elements in unexpected ways. Rare earth element patterns add another layer of complexity. These elements are fractionated during geological processes, meaning their relative abundances change in predictable ways depending on the process involved. Magmatic differentiation, weathering, sediment transport, and diagenesis each produce characteristic rare earth element patterns that geochemists use to interpret depositional environments and source materials. In some anomalous layers, rare earth element patterns deviate from expected natural fractionation trends. Europium anomalies, unusual ratios of light to heavy rare earth elements, and enrichments that don't match any single natural source material appear in sediments that otherwise show no obvious signs of exotic origin. These patterns are subtle and require sophisticated analytical techniques to detect, which explains why they remained unrecognized until recent decades as analytical capabilities improved. The challenge in interpreting these anomalies lies in distinguishing between natural concentration mechanisms and potential artificial sources. Nature can concentrate elements through various processes. Hydrothermal systems circulating through volcanic rocks can leach and redistribute metals, depositing them in concentrated zones. Biological organisms selectively accumulate certain elements, and mass mortality events can create localized enrichments in sediments. Redox boundaries in sediments, where oxygen levels change with depth, can cause metals to precipitate at specific horizons. Diagenesis, the chemical and physical changes that occur as sediments compact and lithify over millions of years, can mobilize and reconcentrate elements. Each of these processes leaves additional geochemical signatures that help identify the mechanism involved. But in ancient rocks that have experienced complex burial and alteration histories, these signatures can become ambiguous or overprinted by later events. What makes certain anomalies particularly intriguing is not any single elemental spike, but the combination of features occurring together. Layers showing rare earth element anomalies also display unusual platinum group metal ratios, carbon isotope excursions, changes in sediment composition, and fossil evidence of environmental stress. The co-occurrence of multiple independent anomalies within the same narrow stratigraphic interval suggests a common cause, some event or process that affected multiple geochemical systems simultaneously. Natural catastrophes like large volcanic eruptions or asteroid impacts can produce such multi-proxy signals, but so could industrial activity followed by civilizational collapse and rapid environmental degradation. The patterns resemble contamination, except the layers containing them were deposited tens or hundreds of millions of years ago, sealed beneath kilometers of subsequent sediment long before humans existed. Rare earth elements, despite their name, are not exceptionally rare in Earth's crust. The geological record preserves these elemental anomalies as faint traces, ambiguous signals that permit multiple interpretations but resist definitive conclusions without additional evidence. Elements like cerium, neodymium, and lanthanum occur in concentrations comparable to common industrial metals like copper or zinc. What makes them rare is their dispersed distribution. They almost never concentrate naturally into economically viable deposits. Extracting them requires processing enormous quantities of ore, and their chemical similarity makes separation extremely difficult. Modern civilization depends on these elements for high-technology applications, powerful magnets in wind turbines and electric motors, phosphors in display screens, catalysts in petroleum refining, components in fiber optic cables and lasers. Any advanced technological civilization would likely discover and exploit rare earth elements, and the industrial processes required to extract and refine them would inevitably release these elements into the environment in concentrated forms. Platinum group metals, including platinum, palladium, iridium, osmium, rhodium, and ruthenium, present an even more striking case. These elements are among the rarest in Earth's crust, with concentrations typically measured in parts per billion. They are extremely resistant to chemical weathering and do not readily form compounds with other elements under surface conditions. In nature, elevated concentrations of platinum group metals occur almost exclusively in specific geological contexts. Certain types of ultramafic igneous rocks formed deep in Earth's mantle, impact craters where asteroid material mixed with terrestrial rock, and volcanic deposits from rare types of eruptions that bring mantle material to the surface. Modern industry uses platinum group metals extensively as catalysts in chemical manufacturing, in catalytic converters that reduce vehicle emissions, in electronic components, and in various high-temperature applications. Plastic and concrete define modern civilization. These materials form the physical infrastructure of industrial society. Buildings, roads, bridges, packaging, pipes, cables, and countless manufactured objects. Humanity produces over 400 million tons of plastic annually and roughly 30 billion tons of concrete. These substances seem permanent, designed to endure for generations. The chemical bonds in plastics eventually break, and the elements return to the carbon cycle, leaving behind at most a faint geochemical anomaly in sediments that might show unusual ratios of organic compounds or trace amounts of synthetic additives like plasticizers and stabilizers. Concrete presents a different problem. This material consists primarily of calcium silicate hydrates formed when cement reacts with water, combined with aggregate materials like sand and gravel. Concrete structures appear robust, but they deteriorate through multiple mechanisms. Water infiltration causes internal corrosion of steel reinforcement, which expands as it rusts and fractures the surrounding concrete. Freeze-thaw cycles in temperate climates progressively damage the material. Chemical weathering dissolves calcium compounds. Acid rain accelerates decomposition. Without active maintenance, concrete structures begin deteriorating within decades and collapse within centuries. Once collapsed, concrete rubble weathers like any other calcium-rich sedimentary material. The calcium silicates in concrete are not thermodynamically stable at Earth's surface conditions. Over thousands of years, they react with carbon dioxide and water to form calcite, the same mineral that comprises limestone. This process essentially converts concrete back into a form of sedimentary rock, chemically indistinguishable from natural limestone deposits. The aggregate materials mixed into concrete, sand, and gravel simply return to being sediment. Steel reinforcement oxidizes completely, leaving behind iron oxide minerals identical to those formed through natural weathering of iron-bearing rocks. Within tens of thousands of years, a concrete structure would be reduced to a layer of calcite-cemented sediment containing scattered iron oxide nodules, a geological feature that could easily be mistaken for a natural hard ground or iron-rich paleosol. The transformation would be complete within a time frame representing less than 1% of the interval since the last mass extinction. Even if concrete structures somehow remained partially intact for longer periods, subsequent geological processes would obliterate them. Sediment deposition would bury the remains under accumulating layers of sand, silt, and clay. The weight of overlying sediment would compact and deform the material. Tectonic processes operating over millions of years would subject buried layers to elevated temperatures and pressures, causing metamorphic changes that would recrystallize minerals and erase original structures. Subduction zones would carry material into Earth's mantle, where it would melt and be recycled into new igneous rocks. Continental collision zones would fold and fracture rock layers, destroying any coherent structures. Erosion would eventually expose and remove uplifted layers, grinding them into sediment that would be transported and redeposited elsewhere. The geological processes that constantly reshape Earth's surface and recycle crustal materials operate continuously, and they would erase any evidence of concrete structures within a few million years at most. The same fate awaits other seemingly durable materials. Metals corrode and disperse. Plastic resists decomposition. Concrete structures stand for centuries. Yet geological timescales operate on entirely different magnitudes, and what appears durable across human lifespans becomes ephemeral when measured against millions of years. Glass, though chemically stable, is physically fragile and would be ground to sand-sized particles indistinguishable from natural silicate grains. Ceramics would survive somewhat longer, but would eventually be broken down through mechanical weathering and chemically altered through diagenesis. Brick structures would collapse and weather into clay minerals identical to those formed from natural rock weathering. Asphalt would degrade like any other hydrocarbon deposit. Even materials specifically designed for durability, like stainless steel or titanium alloys, would oxidize and disperse over geological timescales. The elements would remain, redistributed through natural geochemical cycles, but the manufactured objects would be gone. This impermanence has profound implications for detecting ancient civilizations. If modern human civilization collapsed today and left no survivors, the physical infrastructure that currently covers the planet would be effectively invisible in the geological record within a few million years. Future geologists examining rocks from this period would find no cities, no buildings, no roads, no recognizable artifacts. They might detect geochemical anomalies, unusual concentrations of certain elements in sediment layers, carbon isotope excursions indicating rapid release of fossil carbon, elevated background radiation from dispersed nuclear materials, or anomalous ratios of metals in specific stratigraphic horizons. These would be subtle signals requiring sophisticated analytical techniques to detect and ambiguous enough to permit multiple interpretations. The absence of physical artifacts does not mean the civilization left no trace, but it does mean that the traces would be indirect, geochemical rather than physical, and easily overlooked or misinterpreted without specific knowledge of what to look for. The realization that even our most durable materials would vanish over deep time forces a reconsideration of what evidence might remain from hypothetical ancient civilizations. Researchers cannot expect to find ancient cities or manufactured objects. Instead, they must look for the geochemical fingerprints of industrial activity, elemental anomalies, isotopic signatures, sudden environmental changes recorded in sediments, and patterns of extinction and ecosystem disruption that might indicate artificial rather than natural causes. The search becomes a forensic investigation of subtle signals in ancient rocks rather than an archaeological excavation of physical remains. The disturbing reality is that even our most persistent materials would effectively vanish from the geological record within a time frame that represents mere moments in Earth's history. Plastic, despite its reputation for persistence, faces multiple destruction pathways over deep time. Ultraviolet radiation from sunlight breaks down polymer chains through photodegradation, causing plastic to become brittle and fragment into progressively smaller pieces. Microorganisms, though slow to adapt to synthetic polymers, gradually evolve enzymatic pathways capable of metabolizing plastic compounds. Mechanical weathering from wind, water, and temperature fluctuations physically breaks plastic into microscopic particles. Chemical weathering, particularly oxidation, slowly degrades polymer structures even when buried in sediments. Laboratory studies accelerating these processes suggest that most plastic polymers would degrade to unrecognizable molecular fragments within thousands to tens of thousands of years under typical environmental conditions. Even the most stable plastics, like polytetrafluoroethylene, would not survive millions of years intact. The fragmented remains of plastic would not fossilize in any conventional sense. Fossilization requires replacement of organic material with minerals, a process that works for organisms with structured tissues and hard parts, but not for amorphous synthetic polymers. Plastic particles would instead break down into constituent organic molecules, which would then be further degraded by geological processes indistinguishable from natural organic matter. Some molecular signatures might persist as unusual concentrations of specific organic compounds in sediments, but these would be difficult to distinguish from natural hydrocarbon deposits or biological molecules without knowing exactly what to look for. Nuclear signatures in geological records present one of the most intriguing possibilities for detecting ancient technological civilizations. Unlike organic materials or manufactured structures that degrade and vanish over millions of years, nuclear processes leave distinctive isotopic fingerprints that persist in rock layers for billions of years. Modern uranium deposits lack sufficient fissile material to sustain chain reactions without artificial enrichment. Distinguishing natural reactors from hypothetical artificial ones requires examining multiple characteristics beyond mere presence of fission products. Natural reactors like Oklo display specific spatial patterns. The fission products remain concentrated within the original ore body, distributed in zones corresponding to the reactor core and surrounding rock affected by neutron flux. The isotopic ratios of fission products match theoretical predictions for thermal neutron spectra characteristic of water-moderated reactions. The plutonium isotope ratios reflect production and decay over geological timescales without evidence of chemical separation or enrichment. The reactor geometry, reconstructed from isotopic mapping, shows irregular shapes determined by natural ore body morphology rather than engineered configurations. The timescale of operation, inferred from isotopic systematics, spans hundreds of thousands of years with multiple start-stop cycles controlled by groundwater availability, not the brief operational periods characteristic of artificial reactors. Artificial nuclear activity would leave different signatures. Nuclear weapons testing produces distinctive fallout patterns. The isotopic composition of fission products from weapons differs from natural reactors due to the fast neutron spectrum in explosive fission and the specific design of weapons using highly enriched uranium or plutonium. Weapons fallout contains elevated ratios of certain isotopes like cesium-137 to strontium-90, ratios that differ from natural fission. Nuclear weapons also produce activation products from neutron bombardment of surrounding materials, creating isotopes that would not form in natural reactors. The global distribution of weapons fallout creates a distinct stratigraphic marker, a thin layer enriched in specific radionuclides deposited worldwide during a brief time interval, fundamentally different from the localized, long-duration signature of natural reactors. Nuclear power reactors leave different traces than weapons. Commercial reactors use fuel enriched to 3 to 5% uranium-235, intermediate between natural uranium and weapons-grade material. The spent fuel contains plutonium isotopes in ratios reflecting thermal neutron capture in uranium-238, but also contains transuranic elements like americium and curium produced through multiple neutron captures, elements that form in much smaller quantities in natural reactors. The fission product inventory reflects the specific burnup history and fuel composition. Reprocessing spent fuel to extract plutonium creates waste streams with characteristic isotopic signatures showing chemical separation of elements, a process that would not occur naturally. The waste from reprocessing contains elevated concentrations of certain isotopes while being depleted in others, creating patterns impossible to produce through geological processes alone. These signatures include specific ratios of uranium and plutonium isotopes, unusual concentrations of fission products, and characteristic patterns of radioactive decay that differ fundamentally from natural background radiation. Detecting ancient artificial nuclear activity would require finding signatures that cannot be explained by natural processes. Elevated concentrations of transuranic elements in sedimentary layers far from any natural uranium deposits would be suspicious. Isotopic ratios of plutonium or uranium inconsistent with natural decay chains would indicate artificial enrichment or separation. Fission product distributions showing chemical fractionation rather than in situ decay would suggest technological processing. Spatial patterns inconsistent with natural ore body geometries, such as regular arrangements or concentrations in specific stratigraphic horizons without corresponding uranium deposits, would be anomalous. Global distribution of specific radionuclides in a thin stratigraphic layer, similar to modern weapons fallout but in ancient rocks, would be difficult to explain naturally. The challenge is that these signatures would fade over deep time. Most fission products decay relatively quickly on geological timescales. Cesium-137 has a half-life of 30 years, strontium 90-29 years, making them undetectable after a few centuries. Longer-lived isotopes persist but become increasingly difficult to distinguish from background radiation. Plutonium-239, with a half-life of 24,000 years, would be undetectable after a few 100,000 years. Even uranium isotope ratios, potentially altered by artificial enrichment, would be obscured by natural radioactive decay and geological mixing over millions of years. The most persistent signature would be subtle anomalies in the ratios of stable isotopes produced by fission. Isotopes like certain neodymium and ruthenium isotopes that remain indefinitely but require sophisticated mass spectrometry to measure precisely and interpret correctly. Current research examines uranium deposits and sedimentary rocks for unexplained isotopic anomalies. Beyond Oklo, geologists have identified other locations with evidence of natural nuclear processes, confirming that these phenomena occurred multiple times in Earth's history under appropriate conditions. No confirmed evidence of artificial nuclear signatures in pre-human geological layers has been found, but the search continues as analytical techniques improve and researchers develop better models for what ancient technological activity might look like in the geological record. The challenge lies in distinguishing between natural nuclear phenomena and potential artificial ones, because Earth has produced its own nuclear reactors through geological processes. The most famous example exists in Oklo, Gabon, where natural nuclear fission reactors operated approximately 1.8 billion years ago. These reactors formed when uranium ore deposits became saturated with groundwater, creating conditions that sustained nuclear chain reactions for hundreds of thousands of years. The Oklo reactors consumed approximately 6 tons of uranium-235 through fission, producing plutonium and a full spectrum of fission products identical to those generated in modern nuclear reactors. The discovery in 1972 shocked the scientific community because it demonstrated that nuclear fission could occur naturally under specific geological conditions. The Oklo reactors left unmistakable evidence: depleted uranium-235 ratios in ore deposits, Elevated concentrations of fission products like neodymium-143 and ruthenium-99, and spatial distribution patterns of radioactive isotopes consistent with sustained chain reactions. This discovery established that unusual nuclear signatures in ancient rocks do not automatically indicate artificial activity. Natural nuclear reactors require precise conditions to form. Uranium concentrations must exceed approximately 10% by weight, significantly higher than typical ore deposits. The uranium must be primarily uranium-235, the fissile isotope, which was more abundant in Earth's early history due to its slower radioactive decay compared to uranium-238. Groundwater must be present to moderate neutrons and sustain chain reactions, but not so abundant that it absorbs too many neutrons and quenches the reaction. The geological setting must remain stable for extended periods, preventing disruption of the reactor geometry. These requirements were met during the pre-Cambrian era, when atmospheric oxygen levels had recently increased, allowing uranium to oxidize and concentrate in sedimentary deposits, and when uranium-235 comprised about 3% of natural uranium compared to the current 0.72%. After approximately 1.5 billion years ago, declining uranium-235 abundance made natural reactors impossible. The Ordovician extinction stands as one of Earth's most devastating mass extinctions, yet its cause remains frustratingly unclear even after decades of intensive research. Approximately 445 million years ago, during a geological interval spanning less than 2 million years, between 70 and 85% of all marine species vanished from the fossil record. While glaciation events are not unprecedented in Earth's history, the Ordovician glaciation occurred during a period when atmospheric carbon dioxide levels were significantly higher than present day, perhaps 10 to 15 times modern concentrations. Standard climate models struggle to explain how such extensive glaciation could develop and persist with greenhouse gas levels that should have maintained much warmer conditions. Some researchers have proposed that weathering of newly formed mountain ranges, particularly the tectonic mountains created by tectonic collisions, could have drawn down atmospheric carbon dioxide through enhanced silicate weathering. This process, where carbon dioxide reacts with exposed rock and is ultimately sequestered in marine carbonates, can reduce atmospheric greenhouse gas concentrations over millions of years. However, the rate of carbon dioxide drawdown required to trigger the observed glaciation appears to exceed what silicate weathering could plausibly achieve, even with optimal conditions. The isotopic signatures in the rock record add another layer of complexity. Carbon isotope excursions during the Ordovician extinction show dramatic shifts in the ratio of carbon-13 to carbon-12 in marine carbonates. These excursions indicate massive disruptions to the global carbon cycle, with huge quantities of organic carbon being either buried or released in relatively short time intervals. The magnitude and rapidity of these carbon cycle disruptions rival those seen during other major extinction events like the Permian-Triassic extinction, where volcanic activity and potential methane releases are invoked as causes. Yet the Ordovician period lacks evidence for volcanic activity on the scale necessary to explain the observed carbon isotope patterns. The Ordovician lacks the massive flood basalt provinces that characterize other extinction events. No large igneous province of appropriate age has been identified that could have injected sufficient carbon dioxide or other gases into the atmosphere to drive the observed changes. Ocean chemistry changes during the Ordovician extinction present additional puzzles. Evidence from sedimentary rocks indicates widespread ocean anoxia, where dissolved oxygen levels in seawater dropped to levels insufficient to support most marine life. Anoxic conditions are recorded in black shales deposited during the extinction interval, showing that large portions of the ocean became oxygen-depleted dead zones. The development of anoxia is typically attributed to reduced ocean circulation during glaciation and changes in nutrient cycling that promoted algal blooms and subsequent oxygen consumption during organic matter decomposition. However, the geographic extent and severity of the anoxia appears disproportionate to the glaciation intensity inferred from other evidence. Models of Ordovician ocean circulation suggest that the ocean configuration and continental positions should have maintained relatively vigorous circulation, preventing the kind of widespread stagnation necessary for extensive anoxia. Trace metal concentrations in Ordovician extinction boundary sediments show unusual enrichments in elements like molybdenum, uranium, and vanadium. The extinction occurred in two distinct pulses, separated by hundreds of thousands of years, a pattern that challenges simple explanations involving single catastrophic events like asteroid impacts or massive volcanic eruptions. These metals accumulate in anoxic sediments, confirming oxygen-depleted conditions. But the specific patterns of enrichment and the ratios between different metals sometimes deviate from expectations based on purely natural anoxic events. Some sedimentary sequences show sharp spikes in these metals rather than gradual increases, suggesting rapid onset of anoxic conditions rather than slow environmental deterioration. The biological selectivity of the Ordovician extinction also raises questions. Species living in deep, cold waters suffered disproportionately during the first extinction pulse, despite these environments being relatively stable. Shallow, warm water species were devastated during the second pulse, which aligns with habitat loss from glaciation and sea level drop. However, certain groups showed survival patterns that are difficult to reconcile with simple environmental stress models. Some species with broad environmental tolerances went extinct, while closely related species with narrower tolerances survived, a pattern opposite to what ecological theory predicts. The recovery period following the Ordovician extinction was unusually prolonged. Unlike some mass extinctions where biodiversity rebounds relatively quickly once environmental conditions stabilize, the Ordovician extinction was followed by millions of years of depressed diversity and ecological simplification. The delayed recovery suggests that something fundamental about the marine environment remained disrupted long after the glaciation ended and sea levels returned to normal. This pattern resembles the aftermath of extinctions associated with major geochemical disruptions rather than purely physical habitat loss. What makes this extinction particularly intriguing for the Silurian hypothesis is not merely its severity, but the specific nature of the environmental changes that accompanied it and the lack of clear natural mechanisms to explain those changes. The Ordovician period, spanning from 485 to 443 million years ago, was a time of remarkable biological diversity. Complex marine ecosystems thrived in shallow seas that covered much of the continental land masses. Trilobites, brachiopods, bryozoans, corals, and early fish populated these waters in abundance. Life had not yet colonized land in any significant way, making the oceans the sole repository of Earth's biodiversity. The climate was generally warm with high sea levels, creating extensive shallow marine environments ideal for supporting diverse ecosystems. Then, within a geologically brief interval, the entire system collapsed. The first extinction pulse, known as the Cation extinction, eliminated numerous species adapted to warm, shallow waters. The second pulse, the Hernantian extinction, occurred during a severe glaciation event and devastated cold-adapted species that had survived the first pulse. The conventional explanation for the Ordovician extinction centers on climate change, driven by glaciation. According to this hypothesis, the supercontinent Gondwana drifted over the South Pole, allowing massive ice sheets to form. The glaciation locked water in continental ice, causing sea levels to drop by as much as 100 meters. The loss of shallow marine habitats, combined with cooling ocean temperatures and changes in ocean chemistry, supposedly drove the extinctions. When the glaciation ended and ice sheets melted, rapid warming and sea level rise created a second environmental shock that completed the extinction event. This explanation seems straightforward, but significant problems emerge upon closer examination. The primary issue concerns the speed and magnitude of the environmental changes recorded in the geological record. Oxygen isotope data from marine carbonates indicates that ocean temperatures dropped by approximately 5 to 8 degrees Celsius during the Hernantian glaciation. This cooling occurred over an interval estimated at less than 1 million years, possibly as brief as several 100,000 years. By geological standards, this represents an extraordinarily rapid climate shift. The fossil record contains numerous intervals where entire ecosystems vanish abruptly from the geological record, only to be replaced by completely different assemblages of organisms with no apparent transitional forms connecting them. These gaps represent more than simple preservation failures or incomplete sampling. Another significant gap appears in the terrestrial fossil record during the Carboniferous Permian transition, approximately 300 million years ago. The coal forests of the Carboniferous period were dominated by giant club mosses, horsetails, and early tree ferns, creating swampy ecosystems unlike any modern environment. These forests supported diverse communities of early amphibians, primitive reptiles, and enormous arthropods, including dragonflies with wingspans exceeding 2 feet and millipedes over 6 feet long. During the early Permian period, these Carboniferous ecosystems disappeared and were replaced by very different plant communities dominated by seed ferns, early conifers, and other gymnosperms adapted to drier conditions. The animal communities changed correspondingly, with new groups of reptiles, including the ancestors of mammals, becoming dominant. The transition involved not just species turnover, but fundamental changes in ecosystem structure and function. What makes this transition particularly interesting is the apparent rapidity of the changeover in some locations and the near-complete absence of intermediate ecosystems in the fossil record. Sedimentary sequences show Carboniferous-type ecosystems in one layer and Permian-type ecosystems in layers separated by relatively little time and sediment, with few examples of mixed communities or transitional assemblages. Climate change from warm, humid conditions to cooler, more seasonal climates is typically invoked to explain this transition, but the fossil evidence suggests the ecosystem replacement occurred faster than climate models would predict. The end Permian mass extinction, approximately 252 million years ago, created perhaps the most dramatic gap in the fossil record. This extinction eliminated over 90% of marine species and 70% of terrestrial vertebrate species. The recovery period following this extinction lasted for millions of years, but what makes it particularly relevant to the Silurian hypothesis is not just the severity of the extinction, but the nature of the ecosystems that emerged afterward. The Triassic period following the Permian extinction saw the appearance of entirely new groups of organisms, including the first dinosaurs, the first mammals, and numerous other lineages with no clear Permian ancestors. The fossil record shows a gap of several million years where biodiversity remained extremely low and ecosystems remained simplified, followed by a relatively sudden diversification into forms that dominated the Mesozoic era. Paleontologists searching for the ancestors of these new groups often find their origins obscured by poor fossil preservation during the recovery interval, but the discontinuity between Permian and Triassic ecosystems remains striking. Marine ecosystems show similar patterns of discontinuity, They indicate periods where the continuity of life's evolutionary progression appears fundamentally disrupted, raising questions about what could cause such dramatic discontinuities in the history of life on Earth. The Mesozoic marine revolution, occurring during the Jurassic and Cretaceous periods, saw the replacement of Paleozoic-style marine communities dominated by brachiopods, stalked echinoderms, and simple mollusks with modern-style communities dominated by mobile predators, burrowing bivalves, and complex reef systems. This transition fundamentally restructured marine ecosystems, yet the fossil record provides limited evidence for gradual transitions between these ecosystem types. Instead, many localities show relatively abrupt shifts from one community structure to another. The terrestrial fossil record of the Cenozoic era, spanning the last 66 million years since the extinction of non-avian dinosaurs, contains its own puzzling gaps. The evolution of modern mammalian orders during the Paleocene and Eocene epochs occurred with remarkable speed, producing the ancestors of primates, bats, whales, horses, and numerous other groups within about 10 million years. The fossil record documents the existence of these groups once they were well established, but the transitional forms connecting them to their Cretaceous ancestors often remain elusive or poorly represented. The origin of bats provides a particularly stark example, as the earliest known bat fossils already possess fully developed wings and echolocation capabilities, with few intermediate forms preserved. While conventional paleontology attributes these gaps to a combination of preservation bias, sampling incompleteness, and rapid evolutionary change during times of environmental stress, some gaps display characteristics that challenge these standard explanations. The nature of these discontinuities, their timing, and the specific patterns of disappearance and reappearance deserve closer examination within the framework of the Silurian Hypothesis. One of the most striking examples occurs at the Precambrian-Cambrian boundary, approximately 541 million years ago. The Ediacaran period, spanning from 635 to 541 million years ago, was populated by a unique assemblage of soft-bodied organisms unlike anything seen before or since. These Ediacaran organisms, preserved in exceptional detail in locations like Australia's Ediacara Hills and Newfoundland's Mistaken Point, displayed body plans that bear little resemblance to modern animal phyla. They included frond-like organisms anchored to the seafloor, quilted mattress-shaped creatures, and various radially symmetrical forms. Then, at the Precambrian-Cambrian boundary, these Ediacaran ecosystems disappeared almost entirely from the fossil record. What replaced them were the ancestors of modern animal phyla, appearing during the Cambrian explosion with hard shells, complex sensory organs, and predatory behaviors. The discontinuity is stark. Paleontologists have searched extensively for transitional forms that would connect Ediacaran organisms to Cambrian animals, but these intermediate forms remain largely absent from the fossil record. Some researchers argue that Ediacaran organisms represent failed evolutionary experiments that were outcompeted or consumed by newly evolved Cambrian animals. Others suggest that Ediacaran creatures were not animals at all, but rather represented a separate kingdom of life that went extinct. However, the abruptness of the transition and the completeness of the ecosystem replacement remain difficult to explain through gradual evolutionary processes alone. The fossil record shows that diverse, apparently stable Ediacaran communities persisted for tens of millions of years, then vanished within a geological instant to be replaced by fundamentally different organisms. The Great Oxidation Event, occurring approximately 2.4 billion years ago, represents Earth's first documented mass extinction caused by atmospheric pollution. This catastrophic transformation of the planet's atmosphere was not triggered by volcanic eruptions, asteroid impacts, or geological upheaval, but by living organisms themselves. Oxygen is highly reactive, causing oxidative damage to cellular components and generating dangerous free radicals. Organisms lacking protective mechanisms against oxygen would have experienced widespread die-offs as their habitats became increasingly oxygenated. The geological record preserves evidence of this atmospheric transformation through multiple proxy indicators. The disappearance of detrital uraninite and pyrite from river deposits after 2.4 billion years ago indicates that the atmosphere had become oxidizing, as these minerals are unstable in the presence of oxygen. The appearance of red beds, sedimentary rocks colored by oxidized iron, becomes common in the geological record after this time. Sulfur isotope ratios in sedimentary rocks show a dramatic shift at the 2.4 billion year boundary, reflecting changes in atmospheric chemistry. Perhaps most dramatically, the Great Oxidation Event triggered a severe global glaciation known as the Huronian Glaciation, possibly the longest ice age in Earth's history, lasting from approximately 2.4 to 2.1 billion years ago. The mechanism connecting oxygenation to glaciation involves atmospheric methane. Before oxygen accumulated, methane produced by anaerobic organisms created a greenhouse effect that kept Earth warm. As oxygen levels rose, it reacted with atmospheric methane, converting it to carbon dioxide and water. Since methane is a far more potent greenhouse gas than carbon dioxide, this chemical transformation reduced the greenhouse effect, causing global temperatures to plummet. Geological evidence for this glaciation includes glacial deposits found in rock formations now located near the equator, indicating that ice sheets extended to tropical latitudes. The oxygen catastrophe demonstrates several principles relevant to evaluating potential ancient civilizations. First, it shows that biological or technological activity can create permanent, globally distributed signatures in the geological record that remain detectable billions of years later. Second, it illustrates how life processes can trigger cascading environmental changes with consequences far beyond the immediate effects of the initial activity. Third, it provides a template for identifying pollution signatures in ancient rocks. Sudden shifts in atmospheric chemistry preserved through multiple independent proxy measurements across different rock types and locations. The extinction caused by the oxygen catastrophe was not total. Some anaerobic organisms survived by retreating to oxygen-free environments like deep ocean sediments, isolated pools, and the intestinal tracts of other organisms, where their descendants persist today. Other lineages evolved protective mechanisms against oxygen, eventually developing aerobic respiration that turned the former poison into an energy source. This adaptation set the stage for the evolution of complex multicellular life, as aerobic metabolism provides far more energy than anaerobic processes. The irony is profound. Earth's first mass extinction, caused by pollution from living organisms, ultimately enabled the evolution of all complex life, including humans. Cyanobacteria, through the process of photosynthesis, began releasing oxygen as a waste product into an atmosphere that had contained virtually none of this highly reactive gas. The result was an environmental disaster that wiped out most of the anaerobic life forms that had dominated Earth for over 1 billion years. The parallel to modern industrial civilization is striking and unsettling. If the Silurian hypothesis has merit, and previous industrial civilizations did exist and collapse, their extinction events might have similarly opened ecological opportunities that eventually led to the rise of subsequent civilizations. The oxygen catastrophe proves that catastrophic environmental transformation, mass extinction, and eventual recovery and diversification are patterns woven into Earth's deep history long before humans appeared. Just as human activity is rapidly altering atmospheric composition through carbon dioxide emissions, these ancient microorganisms fundamentally restructured the chemistry of the entire planet through their metabolic processes. The oxygen catastrophe demonstrates that advanced complexity is not required to cause planetary-scale environmental transformation. Simple single-celled organisms, through nothing more than their normal life processes carried out across vast populations and timescales, poisoned the atmosphere for the majority of existing life. This raises a profound question within the framework of the Silurian Hypothesis. If simple bacteria could leave such dramatic signatures in the geological record, what traces would a genuinely advanced technological civilization leave behind? Before the Great Oxidation Event, Earth's atmosphere contained less than 1% of current oxygen levels. The oceans and atmosphere were rich in dissolved iron, methane, and other reduced compounds. Anaerobic organisms thrived in this environment, having evolved metabolic pathways that functioned without oxygen or were actively poisoned by it. Cyanobacteria had evolved the ability to perform oxygenic photosynthesis, perhaps hundreds of millions of years earlier, but initially, the oxygen they produced was absorbed by reduced minerals in the oceans and crust, particularly dissolved iron. Vast deposits of banded iron formations from this period preserve evidence of this process, showing alternating layers of iron oxides precipitated as oxygen reacted with dissolved iron in ancient seas. These formations, found on every continent, represent one of the most dramatic geological signatures ever created by biological activity. Eventually, the oxygen sinks became saturated. Reduced iron in the oceans was depleted, and oxygen began accumulating in the atmosphere. The concentration rose from trace amounts to perhaps 1 to 10% of current levels over a period of a few 100 million years. For anaerobic organisms, this represented a toxic contamination of their entire environment. Computer models simulating the decay of human civilization reveal a disturbing timeline. Within 100,000 years, virtually all surface evidence of our cities, monuments, and infrastructure would vanish from the geological record. This time frame represents a mere blink in geological terms, approximately 0.002% of Earth's history since the extinction of the dinosaurs. Cities built in stable cratonic regions might persist longer in the geological record, but even these areas experience erosion and sediment burial that would obscure surface structures. Researchers have calculated specific decay timelines for recognizable human artifacts. Skyscrapers would collapse within 200 years without maintenance as steel corrodes and concrete degrades. Within 10,000 years, most buildings would be reduced to rubble mounds. Within 50,000 years, these rubble mounds would erode into sediment indistinguishable from natural geological formations. Within 100,000 years, the landscape would show no obvious signs that cities ever existed. Roads and highways would disappear even faster, broken apart by plant roots, frost heaving, and chemical weathering within centuries to millennia. Dams would breach and erode away within thousands to tens of thousands of years. Even Mount Rushmore, carved into granite, would erode beyond recognition within several 100,000 years. The models also examine what might persist beyond surface structures. Certain materials and signatures could potentially survive in the geological record for millions of years. Underground structures including subway tunnels, mine shafts, and basement foundations might leave voids or collapsed structures detectable in rock layers. Concentrated deposits of refined metals, rare earth elements, or synthetic compounds might create anomalous geochemical signatures. Radioactive isotopes from nuclear testing and power generation would decay, but might leave detectable daughter products. Changes in sediment composition, including microplastics and industrial pollutants, might be preserved in certain depositional environments. The key finding from these models is that preservation requires specific, relatively rare conditions. Materials must be rapidly buried in sediment to protect them from oxidation and weathering. The depositional environment must remain stable, avoiding erosion or metamorphism that would destroy or alter the materials. The location must avoid subduction zones and major tectonic activity. Even under ideal conditions, the models suggest that only a tiny fraction of human civilization would be preserved in a form recognizable millions of years later. This creates what researchers call a detection paradox. The longer ago a civilization existed, the less likely we are to find direct physical evidence of it, even if such civilizations were common. A civilization existing 100 million years ago would have left far less evidence than one existing 10 million years ago, which in turn would have left less than one existing 1 million years ago. The models force a reconsideration of what constitutes evidence for ancient civilizations. Direct artifacts and structures become increasingly unlikely to survive as we look deeper into geological time. Instead, researchers must focus on indirect signatures, including anomalous chemical compositions, unusual isotope ratios, sudden changes in sediment characteristics, and unexplained extinction events or climate shifts. These signatures are more likely to survive geological recycling because they become incorporated into rock chemistry rather than existing as discrete physical objects. The computer models ultimately reveal that Earth is remarkably efficient at erasing surface civilizations. The planet's dynamic geology, powerful erosion, and chemical weathering act as a planetary-scale recycling system that grinds structures to dust and disperses their chemical components. The implications for the Silurian hypothesis are profound. If human civilization collapsed today and Earth continued without intelligent life for millions of years, future geologists would find almost nothing of our physical structures. The question becomes unavoidable. How many previous civilizations could have risen and fallen in Earth's 4.5 billion year history, leaving no trace for us to find? Within the vast expanse of geological time, even our most impressive monuments and cities represent temporary perturbations that nature will erase with methodical inevitability. Researchers at institutions including the University of Rochester and NASA's Goddard Institute have constructed detailed models examining the preservation potential of modern materials and structures. These models incorporate factors including erosion rates, tectonic recycling, chemical weathering, and biological decomposition. The results consistently point toward rapid erasure of surface civilization on geological timescales. Steel and iron structures, including bridges, buildings, and vehicles, would oxidize completely within thousands to tens of thousands of years, depending on environmental conditions. Concrete, often considered one of our most durable materials, would crack and crumble as water infiltrates, freezes, and expands, while chemical weathering dissolves the calcium compounds that give concrete its strength. Roman concrete structures surviving 2,000 years seem impressively durable, but geological processes operate on timescales millions of times longer. Even the pyramids of Egypt, constructed from limestone blocks and standing for 4,500 years, would erode to unrecognizable rubble within several million years under natural weathering. Glass, another seemingly permanent material, would shatter and eventually dissolve. Plastics, the most persistent modern pollutant, would photodegrade under ultraviolet radiation, fragment into microplastics, and eventually break down into constituent molecules, though this process might take hundreds of thousands of years. The models reveal that tectonic activity represents the ultimate eraser of surface civilization. Earth's crust recycles through subduction zones where oceanic plates slide beneath continental plates, dragging surface materials into the mantle where they melt and remix. The entire ocean floor recycles approximately every 200 million years, meaning any coastal cities built on oceanic crust would be completely destroyed and subsumed into the mantle. Continental crust persists longer, but mountain building, erosion, and sediment deposition constantly reshape the surface. A city built today in a tectonically active region might be thrust upward into a mountain range, eroded away, buried under kilometers of sediment, or fragmented by faulting within tens of millions of years. Deep within sedimentary rock formations around the world, geologists have discovered something that defies conventional explanation. Thin layers of sediment containing sudden, dramatic spikes in heavy metals and industrial compounds that cannot be attributed to volcanic activity or any known natural process. Mercury concentrations exceed background levels by a factor of 40. Yet the layer contains no evidence of the massive volcanic eruptions that would be required to produce such enrichment. Cadmium and zinc show similar unexplained spikes. The layer's thickness suggests the metal deposition occurred over a period of several thousand to tens of thousands of years, then ceased. Another anomalous layer appears in terrestrial sediments from approximately 35 million years ago in what is now Central Asia. This layer contains elevated concentrations of industrial metals alongside unusual organic compounds that resemble synthetic polymers or combustion byproducts. Chemical analysis reveals complex hydrocarbon chains that do not match known biological sources or natural petroleum. The molecular structures suggest high-temperature processing or synthesis. Conventional explanations involving natural oil seeps or forest fires do not account for the specific compounds present or their concentrations. The layer appears suddenly in the stratigraphic sequence, persists for an estimated 20,000 years based on sediment accumulation rates, then disappears. Perhaps most puzzling are sediment layers containing rare earth elements in concentrations and ratios that suggest refinement and concentration beyond natural processes. Rare earth elements including neodymium, europium, and yttrium occur naturally in low concentrations, distributed relatively evenly in crustal rocks. Concentrating these elements requires sophisticated chemical processing, which is why rare earth refinement represents a major industrial undertaking in modern civilization. Yet certain ancient sediment layers contain rare earth element concentrations elevated by factors of hundreds compared to surrounding strata, with elemental ratios that do not match any known natural deposit. The layers lack the geological context of ore formation, appearing instead as thin horizons in otherwise normal sedimentary sequences. Researchers have proposed various natural mechanisms to explain these anomalies, including previously unknown types of hydrothermal activity, unusual weathering processes under extreme climate conditions, or biological concentration by organisms that selectively absorbed specific metals. Each explanation faces significant challenges. Hydrothermal systems produce characteristic mineral assemblages and alteration patterns absent from these layers. Weathering processes typically fractionate elements in predictable ways that do not match the observed patterns. Biological concentration might explain some metal enrichments, but cannot account for the synthetic organic compounds or rare earth element profiles. The scientific community remains divided on how to interpret these findings. Conservative researchers emphasize that absence of a conventional explanation does not justify invoking extraordinary scenarios. arguing that further research will likely reveal natural processes capable of producing these signatures. More speculative researchers note that the patterns precisely match what would be expected from industrial civilizations, and that dismissing this possibility without serious consideration represents a failure of scientific imagination. The implications extend beyond individual anomalous layers. These anomalous layers appear at various points throughout Earth's geological history, raising questions about their origin that the Silurian hypothesis forces scientists to confront with uncomfortable implications. The standard geological explanation for metal-rich layers involves volcanic eruptions, hydrothermal vents, or asteroid impacts. If these signatures represent evidence of previous industrial civilizations, they suggest such civilizations arose multiple times in Earth's history at intervals of tens of millions of years. This frequency would be consistent with the time required for complex life to evolve, following major extinction events, reach industrial capacity, then collapse and leave evolutionary space for new lineages to develop. The metal signatures also provide insight into what future geologists might find when examining our own era millions of years hence. The Anthropocene, as our current epoch has been termed, is creating a distinct layer in Earth's sedimentary record characterized by plastic microparticles, radioactive isotopes, aluminum from industrial production, and the heavy metal signatures discussed here. This layer will persist in the geological record long after all surface structures have eroded away, serving as a thin but detectable horizon marking the brief flourishing of human industrial civilization. The question becomes whether similar horizons already exist deeper in the stratigraphic column, waiting to be recognized for what they might represent. Volcanic activity releases metals from Earth's mantle. Hydrothermal systems concentrate dissolved metals from seawater, and asteroid impacts can deliver extraterrestrial metals or vaporize crustal rocks. Each of these processes leaves distinctive signatures that allow geologists to identify the source. Volcanic layers contain specific ratios of elements, particular mineral assemblages, and glass fragments called tephra. Hydrothermal deposits show gradual concentration patterns and association with mineral veins. Impact layers contain shocked quartz, spherules, and elevated iridium from the impactor. However, certain anomalous layers contain metal signatures that match none of these patterns. Research published in geological journals has documented sediment layers with elevated concentrations of lead, mercury, cadmium, chromium, and other heavy metals appearing suddenly in the stratigraphic record, persisting for relatively brief periods, then disappearing just as abruptly. The concentrations exceed background levels by factors of 10 to several hundred, yet the layers lack volcanic minerals, impact signatures, or hydrothermal alteration. The temporal pattern proves particularly intriguing: sharp onset, sustained elevation, then rapid decline. This profile resembles the pollution signature that human industrial civilization is currently creating in modern sediments. Lead from gasoline, mercury from coal combustion, cadmium from industrial processes, and chromium from metallurgy are all accumulating in lake beds, ocean sediments, and soil horizons worldwide. Future geologists examining these layers millions of years hence would find exactly this pattern: a sudden spike in heavy metals with no volcanic explanation. The discovery of similar patterns in ancient sediments raises an obvious question that most researchers hesitate to articulate directly. One extensively studied example comes from marine sediment cores in the Pacific Ocean, where researchers identified a layer approximately 15 million years old containing heavy metal concentrations that defy standard explanations. The layer spans multiple core samples across hundreds of kilometers, indicating a widespread phenomenon rather than a localized anomaly. Lead isotope ratios in this layer do not match known volcanic sources or ore deposits in the region. The Cambrian explosion stands as one of the most dramatic events in the history of life on Earth, a period approximately 541 million years ago, when complex animals with hard shells, segmented bodies, and sophisticated sensory organs appeared in the fossil record with startling rapidity. Mass extinction events eliminate dominant lineages and create ecological vacuums that surviving organisms rapidly diversify to fill. The Cambrian explosion exhibits exactly this pattern: explosive diversification into empty ecological niches following a period of environmental upheaval. The Precambrian-Cambrian boundary itself shows evidence of significant environmental disruption, including carbon isotope excursions, indicating major perturbations to the global carbon cycle, changes in ocean chemistry, and fluctuations in oxygen levels. These signatures could represent natural environmental changes, or they could represent the aftermath of industrial collapse on a scale that destabilized planetary systems. The challenge in distinguishing between these scenarios lies in the nature of Precambrian rocks themselves. Rocks older than the Cambrian have experienced over 500 million years of additional geological processing, metamorphism, subduction, erosion, and tectonic recycling. Continental crust from the Precambrian era has been buried, heated, compressed, and chemically altered to degrees that would obliterate most traces of biological or industrial activity. The few areas where Precambrian rocks remain accessible at the surface represent geological exceptions, locations where unusual tectonic stability preserved ancient crust. Even in these areas, the rocks have been altered sufficiently that subtle chemical signatures would be extremely difficult to detect or interpret. This geological overprinting creates what might be called an evidence horizon, a point in deep time beyond which certain types of evidence become effectively undetectable, regardless of whether they originally existed. For industrial civilizations, this horizon might lie somewhere in the range of 500 million to 1 billion years before present, depending on the specific signature being sought and the degree of geological alteration in particular locations. The Cambrian explosion occurs tantalizingly close to this horizon, in a period where some evidence might survive, but much would have been destroyed. The possibility that the Cambrian explosion masks evidence of previous collapse gains support from its sheer improbability under conventional interpretation. The evolution of complex multicellular life required numerous innovations: cell differentiation, intercellular communication, developmental programs, sensory systems, and mineralized structures. The probability of all these innovations occurring nearly simultaneously in multiple independent lineages strains credibility. An alternative interpretation suggests these innovations might not have been new inventions, but rather re-evolutions of capabilities that had existed before. Evolution frequently rediscovers similar solutions to similar problems, a phenomenon called convergent evolution. Eyes have evolved independently dozens of times. Flight evolved separately in insects, pterosaurs, birds, and bats. If complex body plans and hard shells had evolved in some Precambrian lineage, then been lost during a mass extinction, evolution could rediscover these solutions relatively rapidly when conditions again favored complexity. Within a geological instant of roughly 13 to 25 million years, nearly all major animal body plans emerged from oceans that had previously contained only simple, soft-bodied organisms. This sudden diversification has puzzled scientists since Darwin first acknowledged it as a potential challenge to gradual evolutionary theory. This scenario would explain why so many sophisticated features appeared nearly simultaneously. They were not being invented from scratch, but rather re-emerging from the genetic potential that remained in surviving lineages. The Ediacaran fauna itself presents puzzles that fit uncomfortably with conventional evolutionary narratives. These organisms possessed body plans unlike anything before or since, with fractal branching structures and modular construction that some researchers have compared to industrial design principles rather than typical biological forms. Some Ediacaran organisms reached sizes of over a meter in length despite lacking circulatory, respiratory, or digestive systems as far as can be determined from fossils. Their method of feeding, reproducing, and functioning remains largely mysterious. Their sudden disappearance at the Precambrian-Cambrian boundary, coinciding with the appearance of Cambrian fauna, suggests these were not ancestors of modern animals, but rather a separate experiment in multicellular life that failed. Whether this failure was natural or catastrophically induced remains an open question. Research into Precambrian rocks continues to reveal surprises that challenge assumptions about early Earth. Complex organic molecules have been found in rocks over 600 million years old, with structures that some researchers argue exceed what simple microbial life could produce. Trace fossils suggesting motile, bilaterally symmetric organisms appear in rocks that predate the supposed evolution of such body plans. Unusual geochemical signatures in Precambrian sediments hint at environmental conditions that conventional models struggle to explain. Each discovery pushes back the timeline of biological complexity and raises questions about what else might have existed in Earth's deep past. The Cambrian explosion therefore occupies a unique position in both the geological record and the Silurian hypothesis. It represents either the genuine first appearance of complex animal life, or it represents a recovery so complete that it successfully obscured what came before. The very factors that make the Cambrian explosion remarkable, its rapidity and comprehensiveness, also make it an ideal event for masking previous collapses. A civilization that arose in the Precambrian flourished for millions of years, then collapsed in environmental catastrophe would leave its most detectable traces in rocks that have since been subjected to over 500 million years of geological processing. The Cambrian explosion, emerging from this processed and altered geological foundation, would appear to later observers as a beginning when it might equally represent a new chapter following an erased prologue. The Silurian hypothesis introduces a disturbing alternative interpretation. The Cambrian explosion might not represent the first appearance of complex life, but rather a recovery and radiation following a collapse so complete that it erased nearly all evidence of what came before. The conventional explanation for the Cambrian explosion involves a confluence of environmental and evolutionary factors. Rising oxygen levels in the oceans crossed critical thresholds that allowed larger, more active organisms to evolve. The evolution of predation created selective pressure for protective shells and hard parts, which fossilize readily and thus appear suddenly in the geological record. Genetic innovations, including HOX genes, provided the developmental toolkit for building complex body plans. Continental configurations and ocean chemistry favored the preservation of fossils in ways that earlier periods did not. Each of these factors contributes to understanding why complex animals appeared when and how they did. However, this explanation contains an assumption that the Silurian hypothesis challenges, that the Cambrian explosion represents an absolute beginning rather than a resumption. The fossil record before the Cambrian, spanning the preceding 3 billion years of life on Earth, contains primarily microbial mats, simple algae, and the enigmatic Ediacaran organisms that preceded the Cambrian by about 30 million years. The Ediacaran fauna consisted of strange, soft-bodied creatures with quilted body plans utterly unlike anything in modern oceans, most of which disappeared before or during the early Cambrian. The transition from Ediacaran to Cambrian fauna represents not just the appearance of new forms, but the replacement of an entire ecosystem with something fundamentally different. This pattern of wholesale replacement rather than gradual transition raises questions about what might have caused such a dramatic shift. If an advanced civilization had existed in the Precambrian era and collapsed catastrophically, the environmental devastation could have created conditions that reset evolutionary trajectories. Antarctic ice cores contain atmospheric records stretching back nearly 1 million years, preserved in frozen layers that accumulated snowfall by snowfall across countless millennia. Each layer traps tiny bubbles of ancient air, creating a timeline of Earth's atmospheric composition that scientists can read like pages in a book. These natural variations form a baseline against which anomalies become visible. Within this generally regular pattern, several periods show atmospheric changes that defy easy explanation. Approximately 325,000 years ago, during a period known as marine isotope stage 9, carbon dioxide levels rose sharply to concentrations that exceed what orbital forcing and ocean circulation models predict. The spike occurred rapidly by geological standards, reaching levels that would not appear again until the modern industrial era. Conventional explanations invoke changes in Southern Ocean circulation or the collapse of carbon-rich permafrost, but the timing and magnitude remain difficult to reconcile with natural forcing mechanisms alone. The isotopic signature of this carbon dioxide, which can indicate whether it came from volcanic, oceanic, or biological sources, shows characteristics that some researchers find ambiguous, not fitting cleanly into categories that natural sources would produce. A second anomaly appears around 420,000 years ago, where methane concentrations show a brief but dramatic increase that coincides with no corresponding change in temperature or ice volume that would explain enhanced wetland methane production. Methane has a relatively short atmospheric lifetime of about 12 years, meaning sustained high concentrations require ongoing emissions. This spike lasted several decades based on ice core resolution, suggesting a temporary but significant source that activated and then ceased. Tropical wetlands, the primary natural methane source, expand and contract with monsoon intensity, driven by orbital parameters that change gradually over thousands of years, not suddenly over decades. Volcanic emissions can release methane, but volcanic signatures in ice cores show no corresponding sulfate or ash layers during this period. The source of this methane pulse remains unidentified. Perhaps most intriguing are patterns in trace gases that appear in multiple interglacial periods, but vary in ways that natural sources should not produce. Nitrous oxide, a greenhouse gas produced naturally by soil bacteria, shows concentrations during some past warm periods that exceed what soil emissions alone should generate. Nitrous oxide also happens to be a byproduct of high-temperature combustion and certain chemical processes. The isotopic ratios of nitrogen and oxygen within these nitrous oxide molecules could theoretically distinguish between biological soil sources and combustion sources, but ice core samples from these periods show ratios that fall in ambiguous ranges, not definitively natural but not impossible to explain through conventional means. The challenge in interpreting these anomalies lies in the incompleteness of our understanding of natural atmospheric processes. Earth's climate system contains feedback mechanisms and sources that scientists are still working to quantify. Methane can be released from destabilizing ocean floor hydrates, from thawing permafrost, or from changes in tropical wetland extent. Carbon dioxide can be released from warming oceans, from volcanic activity, or from the decomposition of organic matter in soils. These cores have revealed natural climate cycles, volcanic eruptions, and the dramatic impact of human industrialization beginning in the mid-18th century. Each of these sources produces slightly different isotopic signatures, but these signatures can overlap, and ancient samples degraded by hundreds of thousands of years of compression and chemical diffusion may not preserve the subtle distinctions that would definitively identify their origin. This ambiguity creates interpretive space where conventional explanations remain possible but not entirely satisfying. The Silurian Hypothesis suggests an alternative framework for interpreting these anomalies. If an industrial civilization had existed during one of these interglacial periods, its atmospheric emissions would appear in ice cores as spikes in greenhouse gases, changes in trace gas ratios, and potentially in the isotopic signatures of carbon and nitrogen compounds. However, the civilization would need to have existed during a period when ice was actively accumulating in Antarctica, limiting the potential window to interglacial and glacial periods within the last million years. Earlier than this, and no ice record would exist to preserve the signal. Later than this, and the civilization would be recent enough that other evidence would be abundant. The ice core record therefore provides a window into atmospheric history that is both remarkably detailed and frustratingly limited. It captures the last million years with precision but reveals nothing about the hundreds of millions of years that preceded it. For the Silurian Hypothesis, this means ice cores can only test for industrial civilizations in the very recent geological past, a tiny fraction of the time during which such civilizations might have existed. The anomalies that do appear in ice cores might represent natural processes that scientists do not yet fully understand, or they might represent something else, signals from a past that left few other traces. Current research continues to refine techniques for extracting and analyzing ice cores, pushing toward the goal of reaching ice that is 1.5 million years old, which would extend the atmospheric record further back and potentially reveal whether the patterns seen in younger ice continue or whether older periods contain different anomalies. Each new core brings the possibility of finding atmospheric signatures that cannot be explained by natural processes alone, or conversely, of finding that all anomalies fit within the range of natural variation once better understood. However, buried within this frozen archive are anomalies that conventional climate science struggles to explain. Sudden spikes in greenhouse gases, unexplained shifts in atmospheric chemistry, and patterns that bear uncomfortable similarities to industrial signatures, all occurring in epochs long before humans existed. The process of extracting and analyzing ice cores represents one of the most technically demanding operations in Earth science. Drilling teams work in temperatures that plunge below -40 degrees Celsius, operating specialized equipment that can bore through ice nearly 4 kilometers thick without contaminating the ancient air trapped within. The deepest cores from stations like Dome C and Dome Fuji in Antarctica reach ice that fell as snow during the early Pleistocene epoch before the evolution of modern humans. Each meter of core corresponds to years or decades of accumulation, compressed by the weight of ice above into a dense record that must be handled with extreme care to prevent the ancient air bubbles from escaping or becoming contaminated. Once extracted, the ice undergoes meticulous analysis. Scientists measure ratios of oxygen isotopes to determine past temperatures, analyze dust particles to understand atmospheric circulation patterns, and most critically, extract and analyze the air bubbles themselves to determine the precise composition of the atmosphere at the time that snow fell. This analysis has produced a remarkably detailed picture of how Earth's atmosphere has changed across ice ages and warm periods, revealing the natural rhythms of planetary climate. Carbon dioxide levels have oscillated between roughly 180 parts per million during glacial periods and 280 parts per million during warm interglacials, driven by changes in ocean circulation, vegetation coverage, and orbital variations that affect how much sunlight Earth receives. Methane levels have similarly fluctuated in predictable patterns tied to wetland extent and tropical precipitation. Determining what evidence would conclusively prove an ancient industrial civilization existed requires moving beyond speculation and establishing specific, testable geological signatures that no natural process could produce. These isotopes decay over time, with half-lives ranging from decades to millions of years, meaning that after sufficient time, even this evidence would fade. Plutonium-239 has a half-life of 24,000 years, meaning that after 10 million years, virtually none would remain detectable. However, the daughter products of these decays would persist, creating isotopic anomalies in lead, bismuth, and other stable elements that could potentially be traced back to artificial nuclear reactions if the ratios were distinctive enough. The third signature involves stratigraphic patterns that indicate rapid global industrial activity. A genuine industrial civilization would leave a layer in the geological record marking its existence, a boundary where multiple indicators appear simultaneously across the planet. This layer would show synchronized spikes in carbon isotopes indicating fossil fuel combustion, increases in heavy metals like lead and mercury from industrial processes, changes in sediment composition reflecting deforestation and agriculture, and potentially elevated levels of nitrogen compounds from fertilizer production. The key word is synchronized. Natural events like volcanic eruptions or asteroid impacts can create global layers, but they produce different signatures. The Cretaceous-Paleogene boundary that marks the dinosaur extinction shows iridium concentrations, shocked quartz, and spherules from vaporized rock, signatures of an impact. A volcanic event produces sulfur compounds, ash layers, and basaltic minerals. An industrial civilization would produce a combination of signatures that no single natural event creates: fossil fuel carbon, industrial metals, synthetic compounds, and potentially nuclear isotopes, all appearing together in a thin stratigraphic layer that can be traced across continents. The fourth signature involves the geographical distribution of anomalies. Industrial activity concentrates around population centers, manufacturing regions, and resource extraction sites. If ancient industrial civilization existed, certain locations would show more intense signatures than others. Sediments near ancient coastlines where cities might have stood could contain higher concentrations of industrial markers than sediments from remote ocean basins. Mining regions would show evidence of large-scale excavation and processing of ores, leaving distinctive patterns of disturbed geology and concentrated waste products. The challenge lies in the fact that plate tectonics constantly recycles Earth's crust, subducting ocean floors and uplifting new mountain ranges, making it difficult to identify specific locations where ancient cities might have stood. However, certain stable continental regions called cratons have remained relatively undisturbed for billions of years. If industrial signatures appeared in sediments preserved on these cratons, their geographical patterns might reveal the distribution of ancient civilization. The fifth signature involves the rate of change in geological markers. Natural climate changes driven by orbital variations, volcanic activity, or ocean circulation shifts occur over thousands to hundreds of thousands of years. Scientists investigating the Silurian Hypothesis have identified several key markers that would serve as definitive proof, each representing a fingerprint that only technological activity could leave in the rock record. The first and most compelling signature would be synthetic compounds that do not exist in nature. Industrial climate change occurs over decades to centuries. If geological evidence showed atmospheric carbon dioxide rising from 280 parts per million to 400 parts per million over a period of just 200 years, as has occurred in the modern era, this rate of change would be difficult to explain through natural processes alone. The resolution of the geological record becomes critical here. In most ancient sediments, each centimeter represents hundreds or thousands of years, making it impossible to detect changes that occurred over mere centuries. Only in exceptional preservation environments like varved lake sediments, where each layer represents a single year, could such rapid changes be detected. Finding these high-resolution records from ancient periods and discovering within them evidence of rapid atmospheric or environmental changes would constitute strong evidence for industrial activity. The scientific community continues to refine these criteria, developing increasingly sensitive analytical techniques that can detect smaller concentrations of trace elements and more subtle isotopic anomalies. Each advance in technology expands the range of geological evidence that can be examined and increases the likelihood that if ancient industrial civilizations existed, their signatures would eventually be found. Modern civilization has created thousands of molecules that Earth's natural chemistry never produced. Certain plastics like polyethylene terephthalate, synthetic pesticides like DDT, chlorofluorocarbons that destroyed the ozone layer, and polychlorinated biphenyls used in electrical equipment. These compounds have molecular structures that require industrial processes to synthesize. No volcanic eruption, no biological organism, no natural chemical reaction produces them. If geologists discovered a sediment layer from 100 million years ago containing concentrations of synthetic organic compounds with complex molecular structures, this would constitute proof that could not be explained away. The challenge lies in the fact that these compounds degrade over time. Plastics break down into smaller fragments through photodegradation and mechanical weathering, eventually decomposing into carbon dioxide and water over thousands to millions of years. Pesticides and industrial chemicals similarly break down, their complex molecular structures torn apart by oxidation, microbial action, and chemical reactions with surrounding materials. After 10 million years, essentially none of these compounds would remain intact. However, their breakdown products might persist as anomalous concentrations of specific carbon compounds or as ratios of elements that natural processes would not produce. The second signature involves isotopic ratios that reveal artificial nuclear reactions. Natural uranium contains primarily uranium-238 with a small percentage of uranium-235. Nuclear reactors and weapons use enriched uranium, where the proportion of uranium-235 has been artificially increased, or they produce plutonium-239, an element that essentially does not exist in nature. If geologists found plutonium isotopes in ancient rock layers, particularly plutonium-239 or plutonium-240, this would indicate nuclear technology. Natural nuclear reactors did exist, most famously the Oklo reactor in Gabon that operated 2 billion years ago when natural uranium concentrations were higher, but these natural reactors produce different isotopic signatures than artificial reactors. They create different ratios of fission products and leave distinctive patterns in surrounding rock that reflect the specific conditions under which natural fission occurs. An artificial reactor would produce isotopic patterns that match modern nuclear technology, specific ratios of cesium-137, strontium-90, and transuranic elements that natural processes cannot create. The implications of the Silurian hypothesis extend far beyond Earth's geological record, offering a disturbing potential solution to one of the most profound mysteries in science, the Fermi paradox. This scenario suggests a disturbing pattern that could be universal. Technological civilizations might regularly emerge on planets throughout the galaxy, but they destroy themselves or collapse back to pre-industrial conditions within a geological instant, typically within thousands to tens of thousands of years after achieving industrial technology. The evidence from Earth's own history supports this possibility. Human industrial civilization has existed for approximately 200 years, a time span that represents just 0.0000004% of Earth's history. During this microscopically brief period, humanity has already triggered a mass extinction event, altered the planet's atmospheric composition, depleted critical resources, developed weapons capable of rendering the planet uninhabitable, and set in motion climate changes that could destabilize civilization. If humanity were to collapse tomorrow through nuclear war, environmental catastrophe, or resource depletion, and if the survivors never rebuilt industrial technology, future intelligent species arising millions of years hence might find only the faintest traces of our existence. They would face the same challenge scientists investigating the Silurian Hypothesis face today: distinguishing genuine evidence of past civilization from natural geological phenomena. Applying this pattern universally suggests that the galaxy might be filled not with active spacefaring civilizations, but with the ghosts of dead ones, their remains erased by time and geology. The Fermi paradox asks why we see no evidence of alien civilizations, and the Silurian hypothesis answers, because civilizations do not last long enough to leave permanent marks, and the marks they do leave fade into geological noise within a few million years. This explanation becomes even more compelling when considering the specific challenges of interstellar travel and colonization. Even if a civilization survives its industrial phase and develops space technology, the distances between stars present enormous obstacles. The nearest star to Earth, Proxima Centauri, lies 4.2 light-years away. With current technology, reaching it would take tens of thousands of years. More advanced propulsion systems might reduce this to centuries, but even so, interstellar colonization would require sustained technological capability over immense timescales. If most civilizations collapse within thousands of years of industrialization, they would never achieve interstellar expansion. They would remain confined to their home planets, where geological processes would eventually erase all evidence of their existence. The universe would be populated by countless worlds where civilizations rose and fell, each leaving a brief geological signature that faded away before any other civilization could detect it, creating a cosmos where intelligent life is common but perpetually isolated, each species arising, flourishing briefly, and vanishing without ever making contact with others. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a 1950 lunch discussion, the paradox highlights a stark contradiction between the high probability of extraterrestrial civilizations existing and the complete absence of any evidence for them. The Milky Way galaxy contains an estimated 100 to 400 billion stars, many of them billions of years older than our Sun. Statistical models suggest millions of planets in our galaxy alone should have conditions suitable for life. Given the age of the universe at 13.8 billion years and the relative youth of Earth at 4.5 billion years, countless civilizations should have had billions of years head start on humanity to develop technology, explore space, and leave detectable traces of their existence. Yet when astronomers scan the cosmos with radio telescopes, searching for signals of intelligent life, they find only silence. When scientists examine our solar system for evidence of alien visitation or construction projects, they find nothing. This absence of evidence, despite overwhelming statistical probability, constitutes the Fermi paradox, and it demands explanation. The Silurian hypothesis offers a chilling answer. Perhaps advanced civilizations do arise frequently throughout the universe, but they systematically erase themselves from the historical. record before achieving the capability for interstellar expansion. If industrial civilizations on Earth would become virtually undetectable after just a few million years, the same principle would apply to alien civilizations on distant worlds. The geological processes that erase evidence on Earth operate throughout the universe wherever planets have active geology. Plate tectonics recycles planetary crusts, volcanic activity resurfaces landscapes, erosion wears down structures, and given enough time, even the most durable materials decompose. An alien civilization that rose and fell 500 million years ago on a planet orbiting a distant star would leave no traces that telescopes could detect from Earth. Their cities would have crumbled to dust. Their satellites would have decayed from orbit and burned up in atmospheric re-entry, or crashed to the surface where geological processes buried them, and their radio signals would have dissipated into the cosmic background noise after traveling through space for millions of years. The scientific community's response to the Silurian hypothesis has been measured, rigorous, and surprisingly open-minded, reflecting both healthy skepticism and genuine intellectual curiosity about questions that challenge fundamental assumptions. This research validates one of the hypothesis's core premises, that entire lineages of complex organisms could have existed without leaving detectable fossil evidence. The European Geosciences Union has funded a multi-year project examining sediment cores from ocean floors, specifically targeting layers corresponding to major extinction events and unexplained environmental disruptions. Teams are analyzing these cores for concentrations of synthetic compounds, unusual isotope ratios, and distributions of rare earth elements that would be inconsistent with natural processes. While no definitive evidence of ancient industrial activity has emerged, researchers have identified several anomalies that defy easy explanation, including unexpected concentrations of platinum group metals in Ordovician layers and peculiar distributions of certain organic compounds in Permian sediments that do not match patterns from known volcanic or biological sources. These findings remain preliminary and controversial, with vigorous debate continuing about their interpretation. Perhaps most significantly, the hypothesis has prompted scientists to reconsider how they think about the concept of detectability itself. Researchers at NASA's Goddard Institute for Space Studies, where Gavin Schmidt serves as director, are developing computer models that simulate how different types of civilizations would appear in the geological record based on variables like population size, technological sophistication, energy consumption patterns, and duration of industrial activity. These models reveal that a civilization's detectability is not a simple function of its advancement, but depends critically on specific choices about energy sources, material usage, and geographical distribution. A civilization that existed for 100,000 years but relied primarily on renewable energy and biodegradable materials might leave less geological trace than one that existed for only 10,000 years but burned massive quantities of fossil fuels and produced durable synthetic compounds. The current scientific consensus, if one can be said to exist on such a speculative topic, holds several positions simultaneously. First, there is no credible evidence that any previous industrial civilization existed on Earth. The anomalies identified in various geological layers all have plausible natural explanations, even if some details remain unclear. Second, however, scientists increasingly acknowledge that the absence of evidence is not conclusive evidence of absence, particularly when dealing with timescales of hundreds of millions of years and processes that actively destroy evidence. Third, the questions raised by the hypothesis are scientifically valuable regardless of whether previous civilizations actually existed, because they force researchers to develop more sophisticated methods for detecting industrial activity in geological records, methods that will prove essential for identifying potential biosignatures and technosignatures on exoplanets as astronomical technology advances. When Gavin Schmidt and Adam Frank published their seminal paper on the hypothesis in 2018, they deliberately framed it not as a claim that previous civilizations existed, but as a thought experiment designed to sharpen the tools scientists use to detect industrial activity in the geological record. The distinction matters enormously. The authors were not arguing that dinosaurs built cities or that ancient aliens visited Earth. Instead, they posed a more subtle question. If an industrial civilization had existed on Earth millions of years ago, what specific geological signatures would it leave, and do current methods have sufficient resolution to detect them? This framing transformed a potentially fringe topic into legitimate scientific inquiry, and the response from the paleontological and geological communities has been substantial. Research teams across multiple institutions have begun systematically investigating the questions the hypothesis raises, producing findings that complicate the simple narrative that humanity is obviously Earth's first technological species. Several major research initiatives are currently underway, focusing on different aspects of the problem. At the University of Rochester, geochemists are developing new techniques for analyzing carbon isotope ratios in ancient sediments with unprecedented precision, searching for signatures that would indicate sudden, massive releases of sequestered carbon consistent with fossil fuel combustion rather than volcanic activity or natural wildfires. Their preliminary results, published in peer-reviewed journals, show that distinguishing between these sources is more challenging than previously assumed, and that several unexplained anomalies in the Paleocene and Triassic periods warrant further investigation. Meanwhile, researchers at the Smithsonian Institution are conducting comprehensive surveys of fossilization rates across different geological periods, attempting to quantify exactly how much of Earth's biological history is actually preserved in the fossil record. Their findings confirm that fossilization is extraordinarily rare, with estimates suggesting that less than 0.01% of all organisms that have ever lived left any fossil trace whatsoever. For species that existed for relatively brief periods, perhaps only a few million years, the probability of finding fossils drops to near zero, especially if their populations were small or geographically limited. Thanks for watching this exploration of Earth's hidden history. If this investigation into deep time intrigued you, hit that like button and subscribe for more content. Share this video with anyone fascinated by the mysteries buried beneath our feet.